we're going live.
Yep.
Let's go live. Going live. Wow, hello everyone. Welcome to the CaYPT 2022 final physics match. And we will look at, well, let me introduce myself first. I'm the organizer. My name is Jim. And also we have our timer. That's Dave. He's also in our organizing committee. And today he will be operating our management system, and then he'll also be timing for us. But I'll be the voice and maybe face of the stream. So let's just do a quick check. Let's see. Is everyone from Team Schwarz Children here? I have to mute some people, I think. Who do I need to mute?
I hear the stream.
Roshan. Oh no, I can't mute. Can someone give me co-host?
Oh yeah.
Yeah.
I can do that. Okay, cool.
Thank you.
Yep, we're all just running now.
Okay. Okay, you're all here. Okay. So how about Team UTS Bernoulli? Are you guys here?
They are here. I'll make sure that they're on.
All right. Awesome. Okay, could everyone make sure that when you're not speaking, you're muted? And I mean, you're in the call, so you don't have to look at the stream. So that will reduce echo and stuff, okay? So how about Team VPCI? Are you guys here?
Yeah, we're here.
All right, that's amazing. And now we can begin, perhaps. Dave, wanna
Sure. Yeah,
show
we
us the
can.
system? Yeah.
Okay, cool. So I think both of us need to figure this out together because Andrew's not here.
Correct.
Right. I think we go to selective match.
Can you, like on your streaming account, can you just make sure that your video is full screen?
Oh yeah, sure.
So everyone can see it for our audience out there. Any chat,
Okay,
any likes? No likes yet? I need some likes.
Okay, Jim, we need to figure this out together.
Okay,
what was the first thing he said?
Click admin.
Okay.
Go to super admin.
Yeah, and then stage management, I think.
Stage management, yes.
Selective. I think he did selective first, right? Or is it just straight to
you
final?
go to final.
Okay, final. No, it says not ready yet.
No, planning. Go to planning. Publish. Unpublish the match plan.
Are you sure?
Yes, I am sure.
Okay.
Publish the final plan. Did that do anything?
I think we need to plan it before publishing it.
Okay, sure. Then plan it. Then let's plan it.
View plan. Oh, there we go. Yeah. This is a place. We need to select the teams first.
Yes.
So Schwarz Children, Bernoulli, and then VP. Right.
Correct.
Okay. Then we need to select the jurors. So Neil, Brian. Wait, not Miss Vanderkamp. Carlos isn't here today.
Carlos isn't here today. That's correct.
Sheetal? Yeah, Sheetal's here. Awesome.
Nice.
Liam? Is Liam here? No?
I
Okay,
don't see him.
okay. We'll know in
We
like
should
2
be.
minutes.
We
Yeah,
should. We should
yeah.
have.
Is Michael here?
Yeah, here.
Awesome. Xinyu? Is Xinyu here? No? Okay.
Okay.
Uh,
Can we? Okay. Let me send. Let me send a. Let me send a message to Jer.
Okay, I'll keep going down the list for now. Is Faye here? No? Okay. Is Arthur here? No? Ahmed?
Sorry,
Arthur's here.
it's Arthur, but I'm here, but like I don't think I'll be able to stay for the whole thing. So perhaps it's best if you put
Yeah, okay.
me not here. Yeah.
Okay, so you're not here, but you're here for now. But I won't put you in the system. Okay, and Ahmed, are you here?
Yes.
And you're staying for the entire time, right?
Yes.
Okay, thank you. And then Itzel?
I'm here.
Wonderful. Darby?
Darby's not here.
Okay. Andrew Hardy?
Not here.
Okay.
Not
Utkarsh?
here. Not here.
Okay. Dang?
I'm here.
Wonderful. Spencer? Not
Not
here.
here.
Okay. Rainy? I saw Rainy before. I don't see Rainy now. Okay.
We should have two.
Yeah, Sabrina?
No.
Daria?
I'm here.
No. Oh, yes.
Daria,
Okay,
yeah.
wonderful. Muhammad?
Probably not here.
Okay. Jesse?
I'm here.
Wonderful. Ben?
Ben's not here.
Alex?
I don't think Alex is here.
I saw Alex's score sheet earlier. He was the third juror who wasn't marked, who came late. But okay, cool. I guess he's not here now. Gavin? Not here. Okay.
No.
John?
No, John can't. Oh, no, John. No, yeah.
Yeah.
John's-
Ali Reza?
I'm here.
Wonderful. Jim? Are you judging?
Jim is not judging.
Okay. Benoit?
He can't judge.
Oh, I see. Okay.
Conflict of interest.
Oh, I see. Okay. Sharon? Nope. Okay. Requien? No. Eric
Most likely not here.
and Clara.
Clara is not here.
Okay. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 jurors. So Ryan, if you don't want to judge, like we have enough.
We can take you off.
Yeah.
Ryan, do you want to?
Sorry, what?
Ryan, do you
Oh,
want
okay.
us to take us? Okay.
Yeah, he said.
Ryan. Okay. Okay.
Okay,
Cool.
thanks, Ryan.
Cool. We are good. I
Okay,
think.
so then a room number, I think we just say A for some random
Everyone.
reason,
A student. We choose room A.
and then submit, right?
Submit. Correct.
Okay. And then we go to publish. And then
Final
just
plan,
publish.
Yep.
Yeah. Okay.
Sure.
I assume that when you publish something, it should turn into unpublish, right?
I hope.
Uh,
I really
oh,
do. Oh, you're logged out.
Andrew's system is too secure. It signs me out as soon as like I don't do anything for 10 seconds.
All the jurors, I apologize. You just have to bear with us here.
Yes, I'm sure.
Where is Andrew?
Not with us today.
Can you look at the plan again? Go to view plan again.
Sure.
Close, the least active.
Is plan 6 the final? Oh, wait. It's already released. So we're good, right?
Click on it.
Wait. Yeah.
Oh no, that's not the final plan. That's just the.
This is the, yeah, okay. So we go back to planning, view, plan 6 then.
Yeah. Okay.
There we go. Yeah.
Oh yes, nice.
Okay, so we publish this. So accept and activate, right?
Yep. We're smart
Okay.
enough to navigate Andrew's system.
And then publish.
Publish.
And then publish. There we go. Now it
Nice.
works. Okay, good. It has some
It's way
confirmation.
easier to launch nuclear missiles.
Okay.
Wow, these days this is not something that we can
Yeah.
joke about nowadays.
This is being streamed live.
Okay, so draw a number 1, 2, 3, diagonal matrix, remember?
Right. Okay.
And I will pull out the problems. Schwarz children, you guys are doing unsinkable, is that correct?
Wait,
That
what?
First hit?
What letter is that?
Good question. What letter
That's
is that?
letter C, yes. And that's correct, yes.
Okay, wonderful. UTS Bernoulli?
Because Bernoulli, they're doing droplet explosion.
Which is
I
E.
think. Yes.
Okay. And then VP,
VP, they should
We're
be
doing
doing
equipotential.
equipotential lines,
which is
G.
G. Wonderful. Okay.
Awesome. Gonna
Uh,
check all of them. They're all here.
I hope none of you disappeared.
It's a C major chord.
All right. I think we are good. Let's submit.
Okay.
Yes,
We're ready
awesome.
to
Stage
start.
1. Reporter. Who will be reporting for Schwarz children? Schwarz children, are you there?
Yes.
Was the reporter?
Reporter, wait, are we reporting first or like,
Didn't first place report
Wait.
last?
yeah,
Andrew still hasn't fixed this.
Okay, we will go with this then.
Okay,
Oh,
you guys
so
are
we're
reporting
reporting
first. Yes.
Yes, you will report
Okay.
first.
Reporter will be Tracy.
Okay. Who's opposing from Bernoulli?
Braden Zhang.
Wonderful. And then who's reviewing from VP?
Can you give us one moment?
Yeah, it's a last minute change, so sure.
The reviewer is Stone Yang.
Okay,
Wonderful.
I am monitoring our stream chat. Someone told you to hurry up.
Who's telling me that? What? Okay.
Oof. Oof is telling you that. Let's go. Submit.
Oh. Okay. Okay, you guys have 5 minutes on the timer.
Wonderful. And when they share screen, this wouldn't be pinned anymore.
Of course not.
Correct?
Of course not. Yeah. Okay, so actually to all the teams, because there's a lot more people than in your selected fights, make sure you drag the timer to be like your top choice of what you see on your screen when you share your screen. So that you can see the time, of course.
And we will be keeping time relatively strictly. Okay.
In the meantime, if you would all like to share the stream on your Insta accounts, that would be great. Our CaYPT Insta account is down.
I'm always looking forward for some international viewers, as always. I like these streams a lot because they help us acquire a lot of watch hours, which is nice.
Jim, we're staying here in this room, right?
Yes, just stay in the Zoom call.
Yes, Dennis, there is an order. It appears that Schwartz children will be presenting first.
Just a reminder to all the jurors, now it's for this final round, there is a reviewer. So please make sure you also, fill in the reviewer section. And please drop the score sheet into that Google Drive folder as soon as you complete them, because we will have to verify the scores pretty much on the spot and tell everyone who the winner is. Okay.
Hi, Jim. I don't think I'm able to share screen, like the Zoom
Oh.
settings.
Oh, I need to enable it. Sorry. Can you try now?
Okay, now it works. Thank you.
Okay, wonderful.
Let's begin.
Is everyone able to see my screen?
Yes.
Yes.
Okay, great. Hello, everyone. My name is Tracy from Team Schwartz Children, and today I'll be presenting problem C.
Sorry,
unsinkable
1
disk.
second. Sorry, Tracy. I think we're seeing the PowerPoint, not the presenter
Oh,
view.
sorry. I'm so sorry.
Yeah,
Give me
no
one.
worries. I paused the
Could I-
timer.
Okay.
Yep.
Can you see
Okay,
this?
wonderful. We see it now. Okay, cool. You can start.
Okay, great. Hello, everyone. My name is Tracy from Team Schwartz Children, and today I'll be presenting problem C, unsinkable disk. Let's take a look at the problem statement. It says a metal disk with a hole at its center sinks in a container filled with water. When a vertical water jet hits the center of the disk, it may float on the water surface. Explain this phenomenon and investigate the relevant parameters. The parameters we'll be investigating are jet speed, jet radius, hole radius, disk mass, and secondary parameters of fluid density and viscosity. An overview of the presentation, I'll firstly be going over an introduction, then experimental setup, 3 theoretical models, key parameter interactions, and finally a conclusion. Sorry, my slides are glitching. Okay, so for our phenomenon reproduction, here we can see a 3D printed disk with a vertical water jet inside a large water tank, and we can see that there's stable flotation when the jet is centered and running. However, as the jet becomes off-centered or stopped, the disk sinks. Moving on to our experimental setup, here we have a submersible pump inside a large glass water tank, and this pump is powered by a variable voltage transformer in order to vary the voltage supplied. And here we have a black backdrop with a DSLR camera for imaging and a output nozzle held by a wooden stand. Looking more closely, we have a flow meter integrated into the system with a Arduino DAX system to give us our flow rate, and we have a vertical water jet with a 3D printed disk. This setup allows for fast, consistent flow, which we can use for constant flow rate. However, even with the Variac, only 2 consistent speeds are achievable. Therefore, we resort to our second experimental setup, which is our linear actuator model, where we have a large 500 milliliter syringe, again mounted on top of a large glass water tank. and we have a linear actuator system powered by our stepper motor. We have our stepper motor that is powered by our DC power supply, microstep driver, and our Arduino controller. And we have a secure pushing mechanism using a lead screw and guiding rods in order to translate the rotational motion into a translational motion, pushing down on the syringe at a constant velocity. And this will give us very controlled, precise flow rates. However, we only are able to achieve low flow rates and small flow radii. Anything outside of this regime, we resort to our third experimental setup, where we again have our integrated flow meter with a Arduino DAC system, and we use an adapter to a conventional sink faucet and a 3D printed nozzle in order to vary flow radii. This will be able to have measured varied flow rates with variable flow radii for anything outside of the other two regimes. Moving on to our discs, we have firstly our precise 3D printed disc on the top row here, and then we have our fender washers, aluminum sheet metal disc, and acrylic sheet disc. And for disc construction, we have a solid 3D printed disc with an indentation for clay distribution in order to vary our mass. And we have a centered hole, which we drill using a vertically aligned drill press to ensure accuracy. And in order to measure our hole radius, we actually track it against a known wire gauge in order to make very accurate measurements. And for the rest of our physical parameters, we have a flow meter for flow rate, digital scale for mass, and a digital caliper for the radius. Some concepts we take from literature, we have our surface tension, water density, atmospheric pressure, and water viscosity. So this leads us to our first theoretical model, which is flow dynamics. So some assumptions that we make for this model is that firstly, the jet does not collide with the edges of the disk. The jet remains vertical, centered, and at a constant velocity. Water is incompressible, and that the tank is large enough to neglect wave effects. Some geometry that we'll use here is big R is the radius of the disk, small r is the radius of the hole, R jet is the radius of the jet, H is the height of the jet from the nozzle, and TD is the thickness of the disk. And we have our x-axis positive pointing down below the surface. Looking at our force analysis acting on the disk, we have our buoyancy pointing up, gravity pointing down, and surface tension pointing up. Here we know that when the buoyancy is less than the gravity, the disk sinks naturally. However, when we add a added jet force on top, we can see that there's actually a upwards additional force provided, which we call Fj. And here we get our net force balance. And therefore, by solving for when the disk floats, we're able to add in our surface tension, buoyancy, and gravity terms. And therefore, we're able to find our force balance for the minimal force needed for a floating disk. Because the jet force is very complex, we're able to decompose it and think about it in two separate ways. Firstly, the opposing flow to the hole, and secondly, looking at additional vortices and turbulence. And we're able to neglect added mass since we assume this is steady fluid motion. For potential flow, we can think of the disk sinking as a water coming through the hole and coming above it, pushing it down to sink. And therefore, we're able to see this pressure difference between the top and bottom of the disk, where we're able to model the velocity of the flow that wants to come through the hole through Bernoulli's and continuity. However, we are able then to calculate the minimum flow rate needed to oppose this velocity that wants to come up, essentially creating a plug using the jet from the top. However, this only works for disks that are barely dense enough for sinking, as jet flow purely opposes the potential flow, and therefore we need to account for additional forces for heavier disks. Moving on, we look at our jet dynamics. We can see that the jet continues to flow after even impacting the water surface, and it's slowed by a drag force, eventually reaching a terminal depth. And we can see that there's a turbulent boundary layer and vortices that will be investigated. In order to find our jet momentum, we're able to consider our jet as a body of variable mass, and using Bernoulli's equation to model jet momentum, we're able to find this equation. And because the jet and the pool are both of water and have equal density, we're able to find a function of the depth of the jet as a function of time. However, we need further boundary conditions to determine the exact location, and therefore we use both Bernoulli's equation and this jet momentum equation to solve for our depth after penetration and our velocity immediately after penetration. And this involves the Froude number, which we define. However, for our conditions where the two densities are equal, the Froude number is very large. Therefore, we're able to simplify this and see that we have our initial depth after penetrating the surface, and we can see that the jet velocity is reduced by exactly half. Therefore, by using these initial conditions, we're able to quantify the jet velocity as a function of depth. And we can see that it asymptotes towards 0 due to shear stress, and it's actually not quadratic drag. Because our Reynolds number for our jet is actually very high and in the turbulent regime, we can take the no-slip boundary conditions between our fast-moving jet and our slow like water outside, and therefore this velocity difference causes vortices to form due to Kelvin-Helmholtz instability, and we have momentum diffusion as gas gets entrained as it penetrates the surface and the vortices expand axially. However, because this actually contributes to the vortices actually contribute to the upward jet force, but it's very difficult to model. Therefore, we resort to empirical modeling using a pressure field that is over the area of the jet, which is a function of the radius and also the jet characteristics. And we're able to isolate each parameter to visualize the pressure field, and we do this experimentally. We can see that jet velocity and force scales linearly, and radius and force actually is exponential as the y-axis is in a log scale here, and we can see that disk and jet force is quadratic. Therefore, because we're able to figure out the scaling for each of these and differentiate in relation to the radius. Moving on to our second theoretical model about hydraulic jump, we can see now we take away that original assumption where it does not actually, now the water does impact the disk, and we can see that there's visible water dispersion and edge effects. Therefore, we have an additional force exerted downwards on the disk, which we can find by solving linear momentum using our previous jet speed analysis, and we add this to our overall net force equation. Then by Archimedes' principle and Newton's third law, we know that there is an additional buoyant force that results because the disk is pushed down further in the water by this force acting on top, and therefore it causes a uniform additional pressure field that is by Pascal's law. And we're able to solve for this by using area and our previous force balance. The disk is able to be in the stable position without sinking because of the hydraulic jump phenomenon, where we have a fast-moving water expanding radially over the top of the disk and a wave boundary layer wanting to flow inward at a slower velocity. And because there's viscous friction against the disk, we have a subcritical region and a supercritical region that meet where the velocity is equal. And here's the additional geometry that we use to actually quantify this jump. And we're able to equate the pressure of the inward wave to the loss of momentum of the outward flow and actually approximate the disk characteristics. And combining with our previous force balance with our pressure field added by the momentum downwards, we can actually find the depth of the disk that it's pushed down by because of this hydraulic jump. And this is actually a function of just jet velocity and jet radius alone. So moving on to our final theoretical model of stability analysis, here we can see that when sometimes when the jet actually flows through the hole, it acts as a stabilizer for the disk movement. And there's a consistent rotation in the axial direction, in this case clockwise. And we can see that the disk sinks when flow becomes off-centered. And here we can see that because there's an uneven force distribution from the uncentered flow, this causes a torque on one side of the disk, and it causes the higher edge of the disk one edge to go down and the higher edge to go up. But because it's in a slanted position, it wants to move towards the disk and actually becomes a self-stabilizing system. However, when this overshoots, you essentially get the flipping of the disk, and therefore we're able to calculate this critical condition of torque where like the torque has to be greater than the opposing torque of the buoyancy and surface tension in order to tip over and sink, which we can see here. And we can see that the offset needed for this critical condition scales linearly with increasing hole radius. So that finishes with my theoretical model. So moving on to our key parameters, we can see that varying disk mass scale has a linear relationship, and we need an increased jet force for heavier disks. We have a quadratic relationship for disk radius and minimum jet force needed, and also a quadratic relation for hole radius and jet force. Varying jet radius also, with varying jet radius, you need less velocity in order to keep the same amount of force in this manner. And overall, we can see that there's a positive correlation with disk mass, hole radius, and disk radius, and negative correlations with jet radius, viscosity, and density. In conclusion, we have three very controlled experimental setups to account for all regimes of this problem. We have thorough theoretical models depicting flow dynamics, hydraulic jump, as well as the stability analysis and flip conditions of this disk. And we have very key parameters with experimental verification about how each of these parameters impact this phenomenon of the disk flotation. Here are my references. Thank you for listening.
Thank you. So 2 minutes for questions from the opposition.
It's on?
Yeah.
Okay. What do you think are the most important parameters in determining whether the phenomenon will occur or not?
I think the most important parameter is the flow rate, and then second to that is the disk mass.
Does the hydraulic jump still occur if the water just goes straight through the hole?
No, we have two conditions. That's what the first model depicts without the hydraulic jump.
How significant do you think the surface tension effect is in the overall phenomenon?
I think unless you have a very light disk that is barely sinking, I think once you have a heavier disk, it becomes pretty much negligible, but we still include it in our force balance.
Okay. Do you think the whole of the disk is needed for the phenomenon to occur?
No, because you can still have the hydraulic jump, but it will be a very unstable system because it doesn't have that stabilizing effect.
How significant is the effect of the thickness of the disk?
The thickness will affect the buoyancy, but in this case, like I think it only really affects it when it's pushed under the water by the hydraulic jump.
If I increase the volume flow rate, does the radius of the hydraulic jump increase or decrease? Or stay the same?
So you increase the volume flow rate, but the velocity, like you increase the velocity essentially by keeping the radius of the jet the same?
Correct, yeah.
The radius of the jump would increase.
Okay. How did you control your water jet speed or pressure?
We were able to measure our water jet speed and radius by using the flow meter, and we're able to measure the radius differences, and basically you calculate it through Bernoulli's.
Thank you. Let's start the preparation period now. Just a reminder to the opposition, just make sure you have your slides up before the timer's up. And Tracy, you should stop sharing now. Thanks. Awesome, you can start.
Hello, everyone. My name is Braden, and I'll be proposing problem C, unsinkable disk for UTS Team Bernard-Lee. So again, the problem statement says a metal disk with a hole at its center sinks in a container filled with water. When a vertical water jet hits the center of the disk, it may float on the water surface. Explain this phenomenon and investigate the relevant parameters. So a few tasks that we determined were relevant to this problem include: 1, construct a controlled and reliable experimental setup that varied multiple different parameters, such as the radius, metal type, and more. 2, analyze the forces acting on the disk and accurately explain the actual origin of the phenomenon. And 3, create an accurate theoretical model that explains the physics behind the phenomenon. And 4, analyze relationships between the key parameters, such as radius, metal disk, flow rate, and more. So as a summary of their report, they provided an explanation for their experimental setup, which included 3 different ones for 3 different scenarios. They provided an extensive force analysis, which took into account many different forces such as surface tension, the buoyancy, and more. And they also talked a little bit about potential flow and other forces or other phenomena, such as especially the effects of turbulent flow on how the disk would float despite this onward jet of water. So a few merits and next steps for this presentation. I thought that they had a pretty stable and well done experimental setup, including 3 different setups for, again, 3 different scenarios for the water jet radius. I thought that their diagrams and animations were pretty good and really helped visualize what was happening to the problem or what was happening to the disk. They had a really extensive force and momentum analysis where they had derived many different quantitative relationships regarding many of the different parameters investigated. And 4, they had an interesting analysis on the potential flow, which was something that I had not considered previously. However, a few possible next steps that I would suggest for the opponent include providing a more intuitive qualitative explanation. So what is the actual reason for the rising force? Like, what is the actual reason for the disk floating? Instead of just throwing a lot of equations at me and expecting me to interpret them like really easily. I think the quantitative analysis, again, was pretty good, but I think they could have gone more into investigating the actual or developing relationships for the actual hydraulic jump radius and the hydraulic jump height, as well as ways they could measure that and compare that to their actual data. So, and finally, again, I think they could have gone a little bit more. I think they could have developed a more comprehensive explanation for why the hydraulic jump actually occurs and how that differs to the situation where there is no hydraulic jump. At this point, I'd like to invite the reporter for a discussion.
Okay, you guys can start.
Hello? Yes.
Hello. Okay. I have a few questions about your experiment first.
Mhm.
So
Would you like me to share screen?
yeah, that would be helpful. Yeah.
Okay.
Okay. So in your experimental setup, how did you control or measure this water jet speed or flow rate?
We used our flow meter, which actually it basically has a turbine on the inside, and by counting the number of turns it has, it outputs a voltage to the Arduino system, and our code compensates for that to turn that into a liter per minute value.
Okay, thank you. You had 3 experimental setups, right? For 3 different
Yes.
scenarios.
Yes.
How do you ensure that your measurements and observations across all 3 experimental setups were the same, since you had different setups, right? So how do you ensure like the data the same, or your observations are the same?
So essentially for the first and the last setup basically is able to have the same range as all of the setups combined. So we're always able to, we have like overlaps in the range in order to verify. And because we use like the same flow meter system for the first and third, though like the data collection is the exact same system. And for the second one, we actually are able to get very, very precise flow rate, because we can basically calculate the velocity of the linear velocity of the pushing motion to basically like 1 or 2 millimeter per precision. So it's very like overall it's just very precise, and like the data matches throughout the entire regime as well.
What was the difference between your second and third experimental setup again?
The second one, this is the linear actuator one. This one essentially we have very, very controlled flow rates, but it's only for small, we're only able to achieve it for low flow rates with small flow radii in order to get into the turbulent regime. So the third one is basically like a compensating for everything, and we're able to vary the radii as well while having a wider range of flow speeds.
Okay, thanks. Can you show me the discs again?
Yes.
Slide 10, slide 10. Okay, you see in this disc, right? There's like this indentation, right? Like the
Yes.
middle is lower than the sides, right? How does this affect this hydraulic jump phenomena? When the
We actually fill it with clay in order to add mass to it. So like when we actually put it into the water, there is no indentation, it's just filled. So we can approximate it to be a cylinder with thickness TD. And in our hydraulic jump analysis, when we isolate for jump height, we actually take that thickness into account here.
Okay, so how does this difference or change in mass distribution affect the forces acting, or the viability of the phenomenon?
For changing mass, like we see here, like for heavier disc, of course, it needs more jet force in order to propel it. So that this means that we either need like faster water or larger radius, basically larger flow rate, in order to make sure you counter that larger gravitational force. But I know like essentially there will be a limit to that, so you just need to find the appropriate force balance for that specific disc.
Sorry, I meant more of like the mass distribution. So if you're adding all the clay on the top, right, does that change whether the phenomenon occurs or the force?
Because we have it's a solid 3D printed disc, when you like fill it evenly, it like we actually put the clay on the bottom side, so the top side is the PLA in order to make our friction for the hydraulic jump easier to solve. So like it's still it's just the bottom that is a clay surface, but then even so, because it's even, I don't think it really like the mass distribution doesn't really affect it since it's solid PLA.
Yeah, okay. On your graph before, you had like mass or something versus force, right? How are you able to measure the force?
We
imposed?
essentially do this by we know that this is minimum jet force. So what we do is we add mass to the disk until it sinks. And we like, of course, there's a limit to how much force that jet is able to. So you find the force by adding mass essentially. And because adding mass will increase the gravitational force, you're able, and you basically start off with a disk that doesn't float or like barely sinks. And you add mass to a point where even with a certain jet, it begins sinking. And then you know that like that increased gravity is going to be equal to the jet force that jet is exerting on it. So you just find that force balance that way.
Okay. Do you think like by using this method, there would be a lot more error if you aren't able to like change the jet force to like really accurate values or really
I think for us, because we do have quite accurate mass and jet jet flow rate measurements, the error wasn't super big of an issue. But it's, yes, if you were to do this, it would be, you would need to be able to control these very well. However, I think like we really, without like a CFD, it's very difficult to actually quantify this this force without like isolating it in this manner.
Okay. I think in your first theoretical model, you showed like this view of the water going down, and then there are like bubbles underneath or bubbles coming up, right? Yeah. What do you think the effect of these bubbles are? And
I think, okay, sorry, continue.
yeah, go ahead. Go ahead.
I don't like, I think like this aeration just occurs because of the dip when it like collides right at the surface. I think like this actually be here when I talk about the turbulence of it, it does causes this shear layer to expand, but I don't think it actually directly pushes on the disk, because like I think the bubbles are just rising up regardless. I don't think that like the magnitude of force those bubbles rising up have versus the gravitational force, I think that's negligible. It's more of just like it actually expands the shear layer, which causes these like vortices to like occur. Essentially, it's part of the vortices.
Okay. And like this is for when the radius of the water jet is smaller than the radius of the hole, right?
Yes, but then this still occurs even when you have the hydraulic jump, because some water is still going in.
Yeah.
Like
What
this occurs regardless.
do you think there's like significant amount of air that would be caused by the water rebounding off the disk? Like,
What do you mean rebounding off the disk?
like it would be bounce if you have like enough volume flow rate, it would probably be bouncing off the disk, right? And it would be
Also, like the stability.
yeah.
Like, of course there is some, but like when you look at the like some of it, it's like it's very self-correcting. This is in real time, so I don't think it's like super important until it becomes unstable like that. But then like for most of the time, I think it's the momentum approximation is good enough.
And before I asked you in the previous section, right? The hole still when the hole is removed, right? The phenomenon still occurs, correct?
Yes. The
Then-
hydraulic jump portion, yes.
Yeah. Then what do you think is the purpose of a hole?
I think the hole is to firstly to provide this like stability in order to make sure it stays around the jet, because it needs to be centered. And if it's not centered, we see the flipping. So if it doesn't have a hole, it's very easily, or like hole or indentation, it's very easily just going to become off-centered and flip over, or just like pop out and sink. However, that's one of the reasons I think the hole is important. However, we can see because the phenomenon still exists without the hydraulic jump, I think the water itself does provide a lifting force as defined in like this FJ here.
Did you experiment with non-circular disks or non-circular?
No.
Just hypothetically, if I change the disk shape to like a rectangle or a triangle or something like that, well, what do you think would happen to the hydraulic jump?
I think the hydraulic jump itself, like the inner hole is still a circle, correct?
Yeah.
I think the hydraulic jump itself, it will still be a radially like accelerating thing. However, once it meets the edges of the disk, if it goes that far, there might be some like different interactions between the wave boundary and the fast moving water. Possibly it might create like uneven forces around the vertices that maybe make it less stable.
Okay. And if the thickness or like
Sorry, I think I should cut you off there. So you have 1 minute to summarize the discussion.
Okay. I think in today's discussion, we talked a lot about how flow rate was controlled in the opponent's experimental setup, especially how the different variables were controlled, including volume flow rate, jet speed, and especially how they measured the force imposed by the water jet. That was of particular interest to me. We also discussed the effects that changes in the disks would affect the phenomenon, such as the shape, the curvature potentially, even the metal composition or the mass distribution. Finally, we also discussed how bubbles in the phenomenon could affect the phenomenon, how bubbles could affect the phenomenon, especially surface tension. And we both agreed about how the hole is not necessary in the problem and discussed the purpose of the hole. Thank you to the opponent and thank you to the judges.
Okay, thank you. The reviewer now has 3 minutes to ask questions to both the reporter and the opponent.
All right, so thank you so much for the reporter for the great presentation, and thank you to the opponent for leading the very fruitful discussion. So first I want to ask a question to the reporter. So you mentioned the hydraulic jump. Were you able to theoretically predict the radius and the height of this hydraulic jump?
Let me find it. By equating the pressure, the inward wave, and the loss of momentum, yes, if we were to isolate for the height and for the radius of the jump, we would be able to find that.
Okay, I see. And were you also able to account for turbulence? As I know you mentioned that earlier, were you able to quantitatively account for that in your theory?
Quantitatively, we do that by mapping it to the pressure field, which we need to isolate experimentally because it's pretty much impossible to find the actual eddies and vortices using theory alone.
I see. All right, thank you. And how do you believe the turbulence might affect the hydraulic jump?
I think the turbulence itself, just like a high Reynolds number, you mean?
Yes.
Okay, that would just mean that the layer on top, so the fast moving water on top will just move faster, I think, for that. So that means the radius would increase because the wave boundary like that, it would need more friction essentially to be able to meet that slower velocity. However, I think when you incorporate the effects underneath the disk, there are it's like the hydraulic jump is supplemented by the flow that goes through the hole.
I see, thank you. And to the opponent, do you agree with this?
I would agree with this as well. Yeah.
All right. So also to opponent, you mentioned disk shape and how that might affect the hydraulic jump. How do you think the curvature of the disk's edge? So instead of being a flat, sharp edge, instead it was curved, either convex or concave. How do you think that would affect the hydraulic jump and the phenomenon?
I think it would be increase the hydraulic jump radius. If
on a convex or concave surface?
Convex, I would say. Yeah.
I see, thank you. And to the reporter, do you agree with this?
By convex, do you mean it's like a downwards view?
Yes.
I think for this, it's more complicated because the wave boundary layer would be slightly different because the wave would be trapped under the convex lip. But then when it's concave, essentially, you actually have more fluid buildup from the potential flow, which could add to the mass of the disk. And because there's edge effects due to the vortices, I think it's more complicated than just whether or not the hydraulic jump decreases or increases radially.
I see. Thank you. Thank you so much.
Thank you. 2 minutes for the reviewer to prepare. Okay, please share your screen, starting the timer.
Yep, hold on. All right, can everyone see my screen?
We can see the browser. Are you in presentation mode?
I am.
Okay, now we see it. Yep, you can start.
Okay, cool, awesome. Okay. Hello everyone, my name is Stone Yang, and today I'll be reviewing on problem C, unsinkable disk. So I'm beginning with the problem statement. It says, a metal disc with a hole at its center sinks in a container filled with water. When a vertical water jet hits the center of this disc, it may float on the water surface. Explain this phenomenon and investigate the relevant parameters. So given this problem statement, we have identified 4 key tasks that we believe that the reporter must complete to successfully fulfill this problem. First is to construct a reliable experimental setup to reproduce the phenomenon and qualitatively explain the phenomenon's origins and the disk's ability to float, then to theoretically predict the behavior of the disk and how relevant parameters affect it. So just a summary of the report. Given these tasks, we believe that this problem is partially fulfilled. So just a quick summary. The report's theory began with fluid dynamics. Then they went on to quantify the hydraulic jump and the stability with experimental confirmation for like jet force, disk depth, and jet radius. So some merits of the report was that, some merits of the report was that they had a very robust experimental setup and varied many different key parameters. They also had good theoretical considerations with sufficient experimental data and theoretical verification for lots of different parameters. However, I do believe that there was insufficient investigation of hydraulic jump quantitatively, such as the disk radius and height. And I believe this was brought up by the opponent as well. There's also limited qualitative explanations as a phenomenon and how it actually occurs, which I believe was also brought up by the opponent. And there's also lacking consideration of different shapes and of the disk and also different fluids. A summary of the opposition, some key insights that the opponent brought up were the lack of qualitative explanations, insufficient explanation for the origins of the phenomenon, and also minimum theoretical investigation into the hydraulic jump. All of these that we do agree with. So next, moving on to the overview of the discussion. Sorry, I think my computer's frozen. Yeah, okay. So one point that the opponent brought up was that the mass distribution caused by adding clay to the bottom might have affected the phenomenon, and the reporter replied that the mass distribution is not affected too much due to that a robust construction of the actual disk. And I agree with the reporter that the mass distribution will not greatly affect the phenomenon as it was used evenly throughout, and the consistency of clay is genuinely pretty consistent. The next point raised by the opponent was that the formation of bubbles has an effect on the phenomenon. And the reporter's response was that it causes the shear layer to expand, causing vortices. However, this has a minimal effect on the phenomenon. I slightly disagree with the reporter in the sense that it does affect the shear layer, and that at lower velocities, does this have a low effect. However, at high velocities, there will be a greater effect of turbulence, which introduces more vortices and thus more bubbles under the disk. And this also increases with larger holes in the disk as well. So let's say if this was a large hole and a very high speed from the water jet, will introduce considerable amount of bubbles to actually affect the phenomenon. And lastly, a point brought up by the opponent was that he inquired about the importance of the hole at the disk. The reporter responded that the hole is necessary for stability, but not for the hydraulic jump. And we do agree with this, that the hole is very important for the stability of the disk in this experiment. Thank you. Thank you.
Okay, thank you. 2 minutes for concluding remarks from the reporter.
Great. I would first like to thank both the opponent and the reviewer for that very fruitful discussion, as well as the very interesting points raised during the questioning period. So to review what we talked about during both the discussion as well as the review period. So firstly, the opponent and I reviewed the experimental setup, clarifying how we measured variables within them and keeping our measurements consistent between all of them. I believe that our setup is robust enough in order to make, and with our data, it is consistent through all three regimes. And we also clarified how the mass distribution was calculated and how we use that to determine to isolate our jet force. And we talked about how we determined the mass and how this was evenly distributed on top of our disks. We then moved on to clarifying the effect of the bubbles and aeration and how this turbulence actually affects the disk. And I think that even though the air caught from the water flowing through the top is visible, I think that because like the bubbles themselves sticking to the bottom of the disk, while they do have the effect of increasing turbulence, I think that it's the turbulence and vortices that actually cause this effect. The bubbles themselves rising do not provide that significant of a lift force. And finally, we explored the effects of changing outside disk shape. I think this could be an interesting way to extend. However, it probably the principle of it would be the same, except for the area you integrate across for the force. And for the reviewer, we confirmed the prediction of the hydraulic jump, and we talked about how we clarify this effect for turbulence on the hydraulic jump. I believe that with our momentum and pressure forces, we are able to isolate for parameters of the hydraulic jump, even though we prioritize the disk depth. And I think it was very interesting that we could brought up the question of the curvature, which I think is good for further investigation. Again, thank you everyone very much.
Thank you. Okay, so let's start with questions from the jury. If you have a question, just unmute yourself and ask. And if it starts to get too hectic, then we can do the whole thing where you send a message in the chat and then I call on you. But for now, just unmute and ask your question.
Could I ask a question about your error bars for the reporter? So would you mind sharing your plot that had like your data, like I think orange crosses and it was like a blue curve?
Yes. Which graph?
Keep going down. Can you keep going down? I think it was a little later on.
Oh, the key parameters. Okay.
Yeah.
Which slide?
I remember there was a plot you had where it looked like the error bars on the X and Y are like the same. And I just wanted to ask about that. But I don't remember which slide it was now. Yeah, I think it was this one. So I was wondering, it seems like your errors are like the exact same on both sides. Is that just like?
Because the reason we do this is because the reason it's like this is because we find the jet force by increasing the mass. So like the mass measurement is just from the scale. So like it's just the same measurement technique used there.
Okay, all right, sure, thanks.
I want to follow up on that from Michael's question. Is the jet force something you derive from like the model, or is it like you directly measuring the jet force?
We directly measure the jet force.
Okay, thank you, that makes sense.
Okay, let me ask one question. What do you think is the effect of the smoothness of the surface of the disk on any of these quantities you measured, any of the parameters? And the second,
sorry, sorry, go ahead.
No, you go ahead. I have two questions.
Okay, for the smoothness, I think it doesn't really affect it when like it doesn't hit the disk. So I think it's mostly in terms of the hydraulic jump. So for the hydraulic jump, the radius of the jump is basically dependent on this force balance between the slower wave layer boundary coming inward and the faster moving velocity that like expands on the surface of the disk. So if you have you have viscous friction against the disk. So the more rough your disk is, the radius of this hydraulic jump effect would basically decrease.
Okay, and the second one is, in sense of curvature, do you think if the curvature is symmetrical all around this radially, technically, then do you think it has any effect, any significant effect on the result, or would not have any effect?
Like you mean, so there's a lip on the disk essentially, right?
Like if it's like radially, you have a curvature, which let's say it's more like a convex or concave surface rather than being, twisted. Do you think this kind of symmetrical curvature would have any effect?
So like by twist, what do you mean? Sorry, I just need to clarify. What do you mean by twisted?
A twisted means you don't have a symmetrical convex. You rather have a convex, but some. Okay, how should I explain it? Like one side is moved up and the other side is moved down. Okay, think like that. Asymmetrical distortion in the shape.
So like one side curves up and one side curves down, like a kind of like
kind of like more realistic, you know, coin you have, right? I mean, they're not usually fully symmetrical. Sometimes they're one side is a little higher, sometimes another side is lower. Do you think this has any?
I think that would have like, depending on the magnitude of that in relation to the radius of it, there might be, because like as I was saying to the reviewer, there might be a like hindrance of the hydraulic jump if it is like concave up, or like a hindrance of the vortices and the edge effects if it's concave down. It might cause it to be more unstable and like flip over, but that really depends on the magnitude of that discrepancy.
And one last question, because this is really beautiful. I want to know if you can think of any application for such thing. I mean, think about the case of creating energy through, let's say, ocean winds or tidal forces. I mean, do you think you can suggest any application for this kind of calculations?
I think like this wave boundary that you see in the hydraulic jump is present in certain types of like different like naturally occurring waves. So maybe using a similar effect, you could be able to like have like a push like a piston or something in order to generate energy, although I'm not quite sure how like efficient that would be.
Yeah, think about a wave which comes and goes, right? And then you have a concave or convex disk with a hole in it, and then now you are having a reverse basically phenomena, a jet which comes from down and then causes this to oscillate. Can you harvest that oscillation into some, you know, turbine and get energy out of it?
I see. So like kind of like a like flatter like water wheel essentially, right?
Right. I mean, you can.
I think it's possible, although like you would have to tweak the shape of the disc and see how it actually oscillates. I'm not sure if it will actually make like, possibly if you get the parameters just right, it will like continue turning because of the instability. So maybe in that case, it just becomes like a turbine. But then if it doesn't and just oscillates back and forth, that would be like less efficient than a turbine, but it's still possible to collect some sort of energy from it, I guess.
Okay, thank you.
Anyone else with questions?
Yes, I have a question. If you could go back to your experiment description where you showed you used a variable voltage source, right, to change the water flow.
Sorry, yeah. I need to give me 1 sec. I need to share the other screen because I need to present to show the animation. Give me 1 second.
No, you don't have to show me the animation. You used a variable voltage source, right?
Yes.
I think it has a wheel on it. You just turn it clockwise and the voltage output increases.
Yes.
But you mentioned for this setup, you only had 2 consistent speeds.
Yes. I think that was because like the voltage rating for the pump, it just like once you go lower than a certain voltage, it just doesn't really work. So we weren't really able to, even like by varying it, I think it was the whole range of 12 volts. It wasn't very consistent past a certain range.
Okay. All right. Thank you.
Anyone else?
Oh, I have one question for the reviewer. He suggested that if the curvature is studied, I want to know if they have studied this effect of curvature on the result.
If we have personally investigated that,
Yeah, if you have investigated that.
We have not experimentally investigated that, unfortunately.
But what is your prediction?
So I predict that if the surface is convex, then that means the outside water is it's flowing inwards towards the center, where the water jet meets the disk. So that would cause a hydraulic jump to shrink in radius. So that would cause cause the disk to sink slightly because there is less of an effect from the hydraulic jump. But for convex, I believe that the hydraulic jump would be the radius would be much wider because like the water is flowing outwards.
Okay, and the same question for the opponent. They asked if the shape was different, like triangle or square. I want to know if they have investigated the different shapes and what they got.
I did investigate different shapes, such as triangles, rectangles, squares, and I found that since the whole of a disk it's still circular, right? So there wasn't any. The hydraulic jump did not have any noticeable change in the hydraulic jump shape or radius, I would say.
Okay, thank you.
Okay, thank you. So I think we should move on to grading now. So because there's a lot more jurors now, this is the way I think it should work. When you're done with your score sheet, send a message either privately to me or publicly in the chat. Once I see that all the jurors are done with grading, I will go and call one juror at a time, and then you say your report scores, and then I'll go back to the list, and then you say your opponent scores with the partial marks. And then I will input that into the system live. Thank you. Okay, I think we're waiting on one more. There are 9 jurors and I got 8 messages. So
I don't know who to message, but I'm also ready.
perfect. Okay, you can message either me directly or into the public chat. But okay, thanks. I think so. I think we're ready. So for the reporter, Neil.
Yes, I have okay, so I have 1 plus 6 plus 3 minus 0.
And that's a 10, right?
Yeah.
Okay, Sheetal.
620 for a total of 9.
Thank you. Michael.
630.
Thank you. Ahmed.
Sorry, I was unmuted. 620.
So that's a total of 9, right? Yeah. Okay.
Yes.
Thank you. Itzel.
It's 5.5, 2.5, 0.
Thank
Total
you.
of 9.
Okay. Dang.
720.
Total of 10, right?
Correct.
Daria.
7, 2.50.
Okay, we need to round that. Well, it needs to round down. So there'll be a 10. Jesse.
620 for a total of 9, I believe.
Okay, thank you. Ali Reza.
I send it on the message. Okay, so it's 173, 11.
Okay, we need to round that down. So I'm going to reduce it to a 10. So over here. Okay, thank you. So for the opponent, Neil.
1330 for a total of 8.
Okay, thank you. Sheetal?
It's 2320 for a total of 8.
Okay, thank you. Michael?
I have 233 for a total of 9.
Thank you. Ahmed?
1.5, 3, 2.5 for a total of 8.
Thank you. Itzel?
1 to 3.2530 for a total of 9.25.
Wait, sorry. Can you say that one more time?
Oh, so that would be 2,
Oh, 2. Okay, yeah.
3.25,
3.25.
3, and 0.
Okay. We need to round that down to a 9. Okay. Dane?
2330 for a total of 9.
Daria?
Okay, it's 1, 3.5, 2,
And 0?
yeah, 0.
Okay. So it's 7.5. Are you rounding up or down?
Up.
Okay, so that's an 8 then. Jesse?
2330 for a total of 9.
Thank you. Ali Reza?
23309.
Awesome. Okay, thank you. And then for the reviewer, Neil.
I have 1330 for, sorry, no, sorry. 22221 for a total of 10.
And 0 at the last one, right?
Yes.
Yeah, okay. Sheetal?
Okay, so it is 131200 for a total of 8.
Okay. Michael?
I have leading 1, 2, 3, 3, 1 for a total of 10.
Wait, sorry. Is the first one like the one that's already there or like an actual one that you wrote?
The first one to enter is 2.
Okay, so 2, 3.
3, 1, and then 0 and 0. Yeah.
Oh, 0 and 0. Okay, so 2 zeros after. Okay, perfect. That's 10. Okay. Ahmed?
Yeah, it's 2, 2.5, 2.5, 1 for a total of 9, I believe.
And then 2 zeros after?
Yes, yeah.
Okay. Itzel?
2, 2, 2.5, 2. Oh, sorry. Did I do that right? 2, 2, 2.5, 2, 1, and 0. So plus 1 and 0. Oh.
Okay, and then we round down to a 10. Okay. Dang?
Yes, 132100 for a total of 8.
Okay, thank you. Daria?
Okay, 2, 2, 2, 1.5, 0, 1 point, sorry, 0, 0.5, which is 8.
Negative 0.5 at the end, right?
Yeah.
Okay. That's 8. Okay, perfect. Jesse?
223100 for a total of 9.
Thank you. Ali Reza?
1.5, 2, 2.5, 1.5, 0, 0, total 8.5.
Okay, are you rounding up or down?
Up 9.
Okay, so I'll change one of them to a 2. So it's a 9. Okay, perfect. So I guess for the juror comments, I'll just pick someone who gave a high score, someone who gave a low score for all the roles. So Neil, do you want to comment on the reporter?
The reporter made a very good effort for the theoretical and showed as much as they could for the experimental. I understand that because of the way pumps work, you cannot just keep lowering the voltage and expect the pump to still spin. And so, yes, I was impressed by changing the setup because of the limitations of their first experiment.
Thanks. Okay, Jesse.
Is this for the reporter still?
Yeah, for the reporter.
Okay. I really liked how slick the experimental design was. It was a really good use of technology and tools to remove human error. And I just thought that the presentation discussion of a complicated topic like fluid mechanics was really done well.
Awesome, thank you. Michael, do you want to comment on the opponent?
I'll let someone else comment.
Okay. Let's give a 9. Itzel?
I think they did a very good job explaining a pretty complicated subject for a high school student, and I think they gave very good ideas and had a very good way of presenting things. So I really enjoyed their presentation.
Great. I don't think there's much variance. I think we can just go on to the reviewer. Michael, or actually, yeah, Michael, you gave one of the highest scores for reviewer. Do you want to comment on that?
Oh, yeah, I mean, I thought he did a really good job. There's nothing that I would really suggest to add, so that's why.
Perfect. Thank you. And then Daria, you gave one of the lowest scores for reviewer. Is Daria there?
Yes, I'm here.
Yeah, could you just comment on the reviewer?
Oh, yeah, sure. So for the reviewer, it was really great, but I had a point. I believe someone asked that the reviewer asked someone about something, but they didn't do that part of the experiment. So I was wondering if that question was proper. Yeah, that was my main concern. But the rest, it was really good.
Okay, thank you. So I'll submit the scores now. So it's 5:28. We can take a break until 5:35. So it's like just about 5 minutes, and we'll start with stage 2. Thank you.
For all the jurors, please make sure to submit your PDF copies to Google Drive. Thank you.
Okay, let's get everyone back here and start the second stage. So from UTS Bernoulli, who's going to be reporting?
Okay, first of all, we're presenting problem E, droplet explosion.
Interesting. Is it that you just told us the wrong? Okay, is VP presenting equipotential?
VP is presenting equipotential.
So we reverse the problems.
Pretty sure you entered it correctly.
I think like I entered it in front of everyone, right? So
Andrew's system of it.
Okay. Okay. So I guess we just move on as if nothing happened and we pretend we're doing droplet explosion.
We should just continue with our final because the problem letter or name does not really matter. It's the content that matters, right? So minor bug in our system, but I hope everyone could understand. So we will just continue as long as they don't do the same problem, which we will not allow them to. So yeah, and we will also check that no one person go on stage twice.
Yeah, please make sure that all the teams. Yeah, okay, cool. So from UTS Bernoulli, who's presenting droplet explosion?
Reporter is Shuyu.
Perfect. Who's opposing from VP?
Sean Gan.
Great. And then who's reviewing from Shorts Children?
Kevin will be reviewing.
Great. Okay. Let's start. Okay, you have 5 minutes to get your screen share set up. Okay, you may begin.
All right. Hi, my name is Shayu, and I'm representing UTS Team Bernoulli on problem E, droplet explosion. So the problem statement reads, when a drop of a water mixture is deposited on the surface of a hydrophobic liquid, the resulting drop may sometimes fragment into smaller droplets. And it asks us to investigate the parameters that affect the fragmentation, so the number of droplets, and the size of the final droplets. And so parameters I determined as being relevant are foremost the initial concentration of alcohol, as well as the initial drop volume and the type of oil. All right, so first I'm going to be starting with a reproduction of the phenomenon. Here we see an oil bath and a pipette that is depositing the water alcohol mixture onto the bath. And we note that at first the matter droplet spreads. It then reaches a max radius, at which point it starts fragmenting into smaller droplets. It maintains this max radius for some amount of time before at some point the rim starts receding, leaving behind just the fragmented droplets. So here is my experimental setup. I had a phone filming the oil bath from above, as well as a pipette to deposit the solution, and then a ruler next to the oil bath. And so for this problem, a really important component was actually figuring out a way to quantify the area and the number of droplets formed. And so in order to do that, I used a software called Cell Profiler, and I segmented final images of the fragmented droplets in order to get their pixel area and the number of droplets. And the pixel area I then converted to a centimeter area using the ruler in the frame, sorry. All right, so I'm going to begin by theoretically modeling the initial spreading of the droplet. And so I should say that water has a notably higher surface tension than alcohol. And we can see this because when we put water on oil, it doesn't spread, while alcohol does spread. And so a mixture of the two sometimes spreads and sometimes doesn't. And whether it does is going to depend on something called the spreading coefficient, which essentially compares the force of adhesion or the attraction between the mixture and the oil around it with the force of cohesion, which is the attraction within the mixture. And so essentially, if adhesion is greater than cohesion, the droplet will spread because the spreading parameter is greater than 0. And so from literature, Kayser et al. Found a critical concentration of 35% alcohol, above which the spreading coefficient is positive and the droplet does spread. And when I compare this to my own values, I found a very similar critical concentration, and above 35%, the phenomenon was observed to occur. So alcohol evaporates at a rate that is definitely non-negligible within the time span of our experiment. And so, I'd like to note that the efficiency of alcohol is going to differ at the rim of the droplet and at the center of the droplet due to differing depths. And so at the rim, the concentration of alcohol is actually going to be a lot lower, which leads to 3 effects. The first is that at the rim, there's going to be some recoiling of the droplet from the oil bath because of the high water content, and oil is hydrophobic. The rim of the droplet is going to recede after some time, as I showed in the video earlier. And I'd like to note that the rim concentration remains equal to the critical concentration as it recedes. And finally, there's going to be a surface tension gradient caused by these different concentrations. And this is actually what's going to generate the Marangoni flow. And so here as you can see, as you increase the initial concentration of alcohol, you're able to create a greater concentration gradient between the center of the droplet and the rim of the droplet. And so as I mentioned, this means that surface tension gradient is proportional to the initial concentration. All right, so Marangoni flow. Some assumptions I'm going to be making in my model include that alcohol evaporation occurs at a uniform rate across the matter droplet, that water does not evaporate within the timescale of interest, and that the viscous boundary layer is just going to be the oil depth for an oil depth of 5 millimeters. So as I mentioned before, there's going to be a higher surface tension at the rim because there's a lower concentration of alcohol. And so this means that the liquid at the rim is going to pull more strongly on the surrounding liquid, which is going to generate a liquid flow from the center of the droplet to the rim. And we can actually numerically find the velocity of this flow by setting the Marangoni stress caused by the surface tension gradient equal to the viscous shear stress of the oil. And we arrive at the following proportionality. And when we compare, and so again, as you can see, Marangoni flow velocity is proportional to the magnitude of the surface tension gradient. And so I actually tracked the displacement of paper slips on the surface of the droplet after it had reached its maximum radius. And by taking their velocity and comparing it to predicted values using the equation I showed before, you can see that there is quite a good fit. All right, so now we arrive at, like, I guess the most important part of my model, which is actually explaining why droplets form at the rim of the mother droplet. And this is something that hasn't been explored very much in literature. It's mostly where the literature ends. But by observing the phenomenon, we can come up with a few observations and from there draw some conclusions that are going to form the basis of my theory. So first, we observe that the mother droplet has stopped expanding once it reaches its maximum radius. And multiple fingering instabilities are forming at the rim with wavelength lambda as defined there. And we also note that these fingering instabilities then pinch off to form the droplets that we're interested in. And so based on that first observation that the droplet stops expanding, I conclude that the Marangoni velocity at the rim edge must be equal to 0. And so therefore there must be something counteracting this velocity. And as I mentioned before, we also note that the rim recoils from the oil due to its water content and creates a bulge, which we see both visually and also in literature. And so from there, I conclude that it's actually the capillary pressure in this rim bulge that's balancing the Marangoni velocity. And so numerically solving for like the capillary pressure in the rim, and the acceleration of that actually also has to be balanced by the viscous force, just
I think we have some technical difficulties. I pause the timer until they get back. Oh, okay, you got disconnected for a second.
Oh.
Yeah, I think if you can rewind like 10 seconds, I think you should be good to start from there. Cool. Yeah, like from here.
Okay. So numerically solving for the capillary pressure in the rim, and then also balancing that with the viscous force, which earlier we balanced the Marangoni stress with the viscous stress. So of course we have to balance it here too. And then we are able to solve for the velocity created by the capillary pressure, VC, and setting that equal to the Marangoni velocity, we are then able to solve for the rim radius A as being the following proportionality. And so here are predicted values of rim radius based on the predicted values of Marangoni velocity that we derived earlier. And this is all assuming that the value of H in that equation you see there is equal to 2A, which seems pretty valid to me. And when we compare these predicted values to approximated measures of rim radius from literature, which I believe were found using depth interferometry, we see rough agreement, which seems to indicate that the model is somewhat valid. But the most important thing to note here is that rim radius is going to be inversely proportional to the Marangoni flow velocity. And just intuitively, this makes sense because if you have a higher velocity, you're going to need a greater capillary pressure to stop that velocity. And that means you're going to need like more curvature in the rim bulge, which means a smaller radius. And so, okay, here we get to how that rim radius is actually going to transform into those fingering instabilities we saw before. And so something called plateau-Rayleigh instability theory states that a cylinder of liquid will pinch into droplets due to growing perturbations, with the wavelength of those perturbations being equal to 9 times the radius. And at least locally, we can consider like the rim bulge as being a cylinder. And so qualitatively, you can see how the rim, how those perturbations might transform the rim into the fingering instabilities that we observe visually with wavelength lambda. And so we note that wavelength is going to be proportional to the rim radius we just derived. And so now that we have this wavelength, we can use it to actually determine the fragmentation and size of droplets, because we note that as you increase the wavelength, there's obviously going to be fewer fingers, and that results in a lower number of droplets. While conversely, if you increase the wavelength, that's going to result in a greater diameter of each of those fingers, resulting in a greater droplet size. And so we note that droplet size and fragmentation are related to the wavelength. And so like using lambda is equal to 9A, which isn't quite correct because the rim isn't a perfect cylinder, we are able to sort of estimate or predict for the average area of the droplets. And we do show the same trend as with our experimental values, which is that average area decreases with concentration. All right, so throughout my presentation, I sort of introduced a lot of proportionalities. So just to summarize, increasing the initial concentration generates a greater surface tension gradient, which therefore creates a greater Marangoni velocity. And then that greater Marangoni velocity has to be counteracted by the capillary pressure, which means you're going to have a smaller rim radius, a smaller wavelength, and therefore smaller droplet size and more fragmentation, as you can see stated. And so when we actually experimentally investigate this, we do find that same correlation. As you increase the initial concentration of alcohol, you get more and smaller final fragmented droplets. And so just numerically here, we can see that same trend. You get smaller droplets with a larger initial concentration, and you get more droplets with a larger initial concentration. And I just do want to note that one point at the end, which is sort of an outlier, but I believe that might have just been because there were so many droplets that the imaging was kind of blurry, and so I don't think my segmentation worked properly. All right, so some other parameters we varied are the initial droplet volume, and you can see some pictures here. And when we investigated that quantitatively, we found that the average area of the droplets remained roughly the same even as you increase the initial volume, but it primarily appeared to increase the number of droplets formed, which makes sense. As we varied the oil type and therefore the viscosity, we found that with higher viscosity, you got larger droplets, and with higher viscosity, you got fewer droplets. And finally, it does make sense that sort of droplet size and the number of droplets are inversely correlated. And this is just due to volume conservation of water, because you only have a finite amount. And if you have larger droplets, you're going to have fewer, and vice versa. All right, so just to summarize, here are the key parameters I explored and how they affect fragmentation and the size of the droplets. There was initial concentration, initial volume, and the viscosity of the oil, and how they correlated to each other as well. So in conclusion, I created a replicatable experimental setup, and notably, I also used a semi-autonomous image analysis method to actually quantify the final amount of droplets and their sizes. I had a thorough qualitative explanation of the phenomenon, even going beyond where most literature stops. I did quantitative modeling to predict the rim radius and the size of the final droplets, and I also investigated a wide range of key parameters. Here are my references, and thank you very much for listening.
Thank you. Let's have questions from the opposition.
Yes, could you please go to the slide where you put your experimental setup?
Okay, how do I go to
Or
Sorry.
alternatively, you could just answer verbally. Okay.
Here.
Yes. Did you administer the droplet by hand through a pipette?
Yes, I did.
How were you able to make sure that you actually administer the droplet at a constant rate into the hydrophobic liquid, in this case, oil?
I wasn't able to make sure it was completely consistent, but just I tried to do it the same every time.
Okay. Okay, that's fine. What made you assume that the evaporation of alcohol was constant throughout the entire mother droplet?
Because, well, I assumed that because the surface area is kind of the same, like the area exposed to the air, therefore the evaporation rate is just mainly this area.
Okay, that makes sense. Have you considered any other fluids other than alcohol and water mixtures, or a different hydrophobic fluid? All right, that's fine. Let's see. Can you also please go to the graph where you express the fragmentation real quick? Specifically the rim effect.
Rim radius?
The rim radius, correct.
Where was it? Here.
You meant I noticed one of the many possible the many ones, but theoretical didn't quite fit with your literature values. Could you provide an explanation as to potentially why?
Sorry?
Could you provide an explanation as to potentially why your literature values didn't match your theoretical?
A short answer, please.
Oh, because it's I just created an equation that was proportional. So I didn't expect them to exactly match. I just wanted an order of magnitude match.
Okay.
Thank you. We'll go to 3 minutes of preparation now.
myself share. Mute.
Okay, feel free to start.
Hi, my name is Sean Gann, and I'm representing Victoria Park CI. The problem here is droplet explosion, which is described as when a drop of water mixture, for example, water with alcohol, is deposited on the surface of a hydrophobic liquid. The resulting drop may sometimes fragment into smaller droplets. Investigate the parameters that affect the fragmentation size of the final droplets. Now, of course, given this problem statement that it is, we developed a couple of tasks that we think is important in order to actually solve and present a solution to this problem, including being able to qualitatively explain the nature of the phenomenon, create a controlled, repeatable experimental setup, as well as an accurate method of measuring the droplet sizes themselves, explain the effects of various parameters on the size of the mother droplet and fragments, as well as the limits of the phenomenon, and quantitatively and theoretically predict the size of the mother droplets and its fragments. As a summary of the report presented by the reporter, we believe these tasks have been partially fulfilled, and the reporter has used theoretical analysis of the spreading, the Marigoni effect, and the droplet formation, and has experimentally confirmed this using the verification of the spreading as a whole, a paper slits on mother droplet analysis, and a droplet size measurement. Now, there are merits, especially being able to successfully recreate the phenomenon, good use of cell profile to obtain quantitative data to a very high degree of effectiveness, and thorough qualitative explanation of the phenomenon. However, the experiment measurement was prone to specific errors in terms of its administration. Theoretical models sometimes do not match closely with the experimental values, and lack of the exploration of the limits of the phenomenon. Some next possible steps would be to consider the mediums of other mixtures, lack of including an error analysis bars, and as well as explanations for what deviations occur as a whole. And the experimental setup could be further improved with a micropipette or a motorized injection system, considering the fact that alcohol evaporates very quickly upon exposure to air. Now, some missed physics that could be explored on is the implication of the temperature of the hydrophobic liquid or mixture. The limits of the phenomenon, evaporation or minimum concentration, was not explored as a whole and could provide some valuable insight onto the actual phenomenon itself. Lacks testing with completely controlled setup, which can, and also missed an explanation for the fit model and as well as error analysis. At this time, I would like to invite the reporter up in order to discuss her solutions and her presentation. Oh,
So how do we get back to here? Oh, hi. Sorry,
Okay.
would you like to share my slides?
Not quite right now. I have more of a question first. Did you consider what would happen if we substituted alcohol for a different fluid, such as hydrogen peroxide, or another fluid that's also very relatively volatile?
I did not consider that. No.
What would you think would happen given your equations, though? Because if it's given that hydrogen peroxide evaporates much faster than alcohol, what would you think would happen?
I think if it evaporates faster, the entire phenomenon would just occur on a faster time scale, but just the evaporation rate alone would not be enough to change the size and number of final droplets.
Okay. Did you consider trying to measure the radius of the mother droplet over time, or no?
I did not do that. No.
Okay, that's fine. Because one of the reasons I want to ask this is because the evaporation rate actually affects the growth and the collapse of the mother droplet radius itself. Although, does the theory explain that?
I have theory predicting like the maximum radius of the mother droplet, but not how it changes over time.
Not how it
because I
changes
did
over time.
think that was important to predict the final number of droplets and the droplet
Okay,
sizes.
okay, that makes perfect sense. And that's completely understandable. However, have you also considered what the temperature would have an effect on this, like through the mixture or the hydrophobic fluid?
Well, temperature would affect the evaporation rate, and then it would also affect like the density and surface tension values. But I have those surface tension values and density values in my equations, so it would just be a matter of figuring out how temperature actually affects those, and then changing those values in my equations.
Okay. Of course. You notice you mentioned the Maragoni effect, and I also heard that you mentioned the heat, how heat would change the actual surface tension gradient. This is known as the capillary effect, but can you also provide a little more insight on how if you would compare two different temperature mixtures? Because if you put a very cold substance on a very hot substance, it evaporates almost instantaneously. What if we push the limits to this experience with the alcohol evaporating rather almost instantaneously? How would that affect dispersion?
I mean, you still have like a differing depth profile of the droplet, right? So at the edges, the alcohol will still evaporate a lot faster, and so that will still create the Marangoni flow. Just if in the center it's also evaporating a lot faster, it means that the rim of the mother droplet is going to recede a lot faster as well. And I think because of that, you're going to get less droplets.
Okay, I want to revisit again now I'm going to ask you for you to share your slideshows. I want to revisit the part where you explained the capillary and the dispersion of the droplets themselves.
Sure, let me. Is it this one? Okay, can you see?
No,
So which
the
slide?
one.
Which slide?
The one that had you explained how the droplets actually and fragments actually form at the end, with the capillary equation.
Yeah, sure. This one?
Yes, correct. Now, as for this, you mentioned the fact that we can solve for the actual velocity from this, correct?
Yes. Mhm.
Yes. How would you perceive that? How would you perceive the velocity would actually? Why does it form? No, correction. Why do you think the droplets actually form a specific way, and the reason why this sort of shape specifically forms with the in relation to, well, the actual interfacial forces and surface tension specifically?
Sorry, can you repeat that question? I don't quite understand what you're asking.
Just why specifically a droplet form rather than say if you put a non-hydrophobic liquid and a hydrophobic liquid together, why instead would it not spread out like a puddle, but instead spreads out as a
So you're asking why the rim doesn't just keep spreading out and forms into droplets?
yeah, and why does it form droplets specifically?
Well, it forms, that's actually less this part, and that's more the next part where I talk about like the Plateau-Rayleigh instability. And that's because when you have like a cylinder of liquid, even if you just think of like a jet of water coming, like a stream of water coming out of a tap, like just naturally, it's going to form into droplets because of like these perturbations that grow over time.
Okay. As for your experiment itself, I noted that you did change the concentrations. Were you able to find a very specific concentration where it's the bare minimum for the phenomenon to occur?
Yeah, so I looked at that earlier, which is in like my experimental verification of spreading. And so basically, from literature, they found that critical concentration to be 35% because of the surface tensions of like the oil, the mixture, and the oil mixture interface. And when I compared that to my own data, I found a very similar critical concentration. I think the lowest concentration I was able to observe the phenomenon for was 38% alcohol concentration.
What'd you observe for those that didn't react? They just?
Yeah, you just get one droplet as well. It looks like it says 0, but you get just one droplet, the amount of droplet, and it doesn't spread. And because it doesn't, it also doesn't form into smaller droplets, and instead it just like slowly evaporates, leaving behind just the water.
Excellent. Now, if we take the complete opposite of this and say, let's say we had a 100% concentration of alcohol, which is theoretically impossible because otherwise the dye probably wouldn't work. But how would you think how would you predict these scenario would be then?
Well, if it's 100% alcohol, it's going to spread initially on the oil, but because you don't create like a concentration gradient because it's all going to be 100% alcohol, you won't get the Marangoni flow, and because of that, I believe it will just evaporate and sort of slowly just all evaporate, but you won't get any droplets fragmentation.
But would the mother droplet spread or no?
It would spread, yes.
It would spread.
As I showed here, if you just have alcohol and you put it on oil, it does spread.
Okay, good. If that's the case as well, I remember you mentioning how you did the slit paper test. I'm actually quite interested in how you were able to consistently perform that test. And correct me if I'm wrong, I do believe that implies that you took a piece of paper and covered the droplets, and then the droplets stayed on that piece of paper, correct?
Sorry, not this one. Here, so it was like very, very tiny slips of paper, and I just like sprinkled them onto the surface of the droplet after it had formed its maximum radius, and I was videoing it from above, and I just like tracked the movement of those slips of paper towards the rim of the droplet.
I noticed you didn't quite do an error analysis on this, even though there's probably a fairly margin of error when you're actually physically applying that. Could you explain the reason why you chose not to, or alternatively, could you explain how, or could you show to me like what error range would you actually expect from this type of method?
I mean, the reason I didn't is because I just didn't. But like the way I actually got the displacement from the origin in centimeters was by having like a ruler in the same picture, and then using that to sort of have like a pixel scale, and then tracking like the pixel distance from the origin. But in terms of error, I guess that would just be the measurement, like the ruler error measurement.
You're not considering the fact that even if you apply the droplets onto the piece of paper, they will spread slightly on the paper due to the volume being a comparison of a 2D projection to a 3D actual volume surface.
Wait, sorry, could you repeat that?
You're not including the possible errors that come from when the droplet actually spreads on the paper, like simpler as when you drop a droplet.
I definitely think there's error here in like my measured values of the
Oh.
Marangoni block. And I actually think that's why my experimental values are lower than the theoretical, is because like the slip of paper on the surface doesn't completely capture the actual velocity of the flow. It's just sort of like carried along a little bit by the flow. But I'm not sure how I would go about quantifying that error.
Okay, and final thing, I noticed you mentioned, I refer earlier in this discussion, we mentioned the fact about the mother droplet radius and how it expands and then collapses. I don't believe you discussed in your presentation how it would collapse. Could you elaborate on that?
Like it collapses because, as I mentioned, there is this critical concentration of, oh, sorry, I'm just trying to get back.
That's right.
It collapses because, as I mentioned, there is this critical like 35% concentration of alcohol. And once the alcohol derivative evaporates to 35%, it's going to just like sort of recoil until and stays constant at 35% as it sort of recedes. And that's sort of. Mhm.
So then at that case, if I'm assuming correctly, the Marangoni effect would actually not be existent anymore, and then the surface tension gradients would actually reverse that, causing the collapse of sorts, correct?
Even as it's receding, I believe there is still a Marangoni flow because the concentration at the center of the droplet is still going to be higher than 35%. So there is still going to be a Marangoni flow. It's just over a smaller distance.
Okay, that's understandable. I do believe we're about to run out of time. That was a very fruitful discussion. Thank you.
Okay, thank you. You have 1 minute to summarize the discussion.
So, as presented, the reporter was able, and I were able to engage a discussion, which we discussed the limits of her theory and her quantitative experiments and results, and we were able to further discuss about the edge scenarios that would happen if there, in terms of like what would happen if we had extreme parameters, as well as further exploring how her experiment was robust or not robust to a degree, as well as her understanding of the theory as a whole. I do believe we're able to engage in a fruitful explanation, and she certainly does demonstrate her competency with the theory that she has. Although it would still believe that we were able to still discuss on the weaknesses of her theory and her experimental data, and further elaborate on that to help further solidify our understanding of the whole on this phenomenon.
Okay, thank you. Let's have questions from the reviewer.
First, I'd like to thank the opponent and the reporter for the fruitful discussion that they made. So to start off, I'd like to give a question to the reporter. What do you think is a good way to measure the surface tension of a droplet?
I didn't actually measure it. I used values from literature. Do you mean like the surface tension between the water alcohol mixture and the air, or between the water?
No, I just mean the surface tension of the droplet. The surface tension gradient of the droplet.
But the surface tension is always between like two liquids. So do you mean between like the droplet and the air, or the droplet and the oil?
I just mean the droplet and the oil.
As I said, I just used values from literature, but I believe there's a way to measure that involves like dripping the liquid out of some type.
Okay, thank you. And to the opponent, do you agree with this?
I would agree. I would choose a slightly different method. Since we can track each of the individual droplets' velocity individually through like a program called Tracker, we can also approximate the volume of the droplet itself by approximating assuming volume of a sphere, and given that a droplet's around the same volume as water, we can calculate the net force acting on it, and then we can calculate the gradient, the net force, and thus the surface tension gradient.
Okay, thank you. Now to the reporter once again, based on your Rayleigh instability model, what do you think is the driving force of this phenomenon?
The driving force of why droplets form?
Yeah.
Well, I mean, a driving force of the phenomenon is the fact that you have this Marangoni flow, which is creating the rim, but then why droplets actually form is because that rim is very unstable, and so it breaks up into droplets.
Okay, thank you. And to the reporter, do you agree with this?
I also agree to extent, although I will be adding that part of the adhesion forces caused, but this is due to entropy forces, which prevent the mixing of hydrophobic and hydrophilic lipids.
Okay, thank you. Based on this, what do you think is the most important parameter, the opponent of the experiment?
The most important parameter I would have to significantly say is the concentration of alcohol, because that determines the evaporation rate and thus the actual surface Marangoni effect, as mentioned by
Okay, thank you. To the reporter, do you agree with this?
Yes, I agree. The concentration of alcohol is the most
Okay.
important one.
Okay, yep, thank you. We also agree with this. And as well, as you increase the height of launching the droplet, right? So let's say you launch the droplet from a ridiculously tall height. What do you think will actually happen to the droplet as it hits the surface? Does it still produce the Marangoni effect? To the reporter.
I think if you drop it from a very high height, it would burst upon contact with the liquid, and so you might not observe the same effect.
Okay, thank you. To the reporter, or to the opponent, do you agree with this?
I slightly agree with this, except for the fact that some of the alcohol might evaporate during the fragmentation as it kind of explodes, which results in droplets that which might actually produce secondary droplet explosions and some fragments that won't.
Okay, thank you.
Thank you. Let's go to the preparation period. Okay, you can start.
Hello, this is Kevin Z from Team Force Children, and today I will be reviewing problem 8, droplet explosion. Oh, sorry. No, I'm already.
We don't see, we only see your Chrome window right now.
Oh, sorry.
Are you presenting?
I'm sorry, just some technical difficulties. Hello, can you see now?
Yes, now we can see it.
Okay, thank you. So restarting again. Hello, my name is Kevin Z from Team Force Children, and today I'll be reviewing problem 8, droplet explosion. So moving on, so some tasks we created for the reporter are that they have to, 1, qualitatively explain the phenomenon, 2, construct reliable experimental setup with reproducible results, 3, explain parameters that affect the size of the droplets, and finally, theoretically predict fragmentation and final droplet size. So based on this, giving a summary of the report, they had thorough theoretical analysis with surface tension, talking about surface tension, Marangoni flow, and droplet deformation, as well as an experimental confirmation with dropping the droplets with a pipette and using cell profiler for imaging. Moving on to the reporter's merits, they qualitatively explained the phenomenon with a preliminary experimental setup, as well as they attempted to model surface tension, Maragoni flow, and droplet deformation. Next, they investigated some parameters involved in the experiment, which they talked about. So some possible next steps are that there was an uncontrolled drop height, drop volume, and drop angle, as well as generally moving the droplet around during the experiment, as well as they did not investigate drop angle, evaporation during falling, and they didn't investigate parameters that affect the formation of the rim, as well as the Rayleigh instability. As well, they didn't provide insight on error analysis and as well as theoretical matching, as the fit did not seem to relate to their experimental when they showed the theoretical. So for some key insights of the opponents, they had experimental error with an uncontrolled setup, and they talked about the possible improvements for the opponents. And they also had a discussion regarding temperature variation, as well as talked about some limits of the phenomenon. And finally, they moved on to talking about experimental error, which we agree with. So the merits are that they talked about the limit of the phenomenon, as well as the impact of the temperature, as well as isolating the discussion about evaporation. And some possible next steps for the opponent are that they could have talked about the impact on shape and size of the droplet expansion, investigating the properties of the materials used, such as wetting and de-wetting properties of the mother droplet, and also investigating the fragmentation, or talking about investigating the fragmentation parameters of the alcohol, such as the parameters that affect the fragmentation of only alcohol. So, wait, sorry, just a technical error. So some points raised by the opponent are that, well, what happens when the alcohol is substituted for other liquids, and as well as the reporter's response was that it won't really affect anything other than scaling the evaporation rate. We partially agree with the reporter in that efficiency of alcohol evaporation would increase, resulting in a greater decrease in surface tension gradients, as well as the point raised by the opponent in that changing in alcohol concentration effect. And the reporter's response to this was no Maragoni effect is created with 100% alcohol is dropped on the oil surface. And we disagree with the reporter in that effect is still 100% present, as when 100% alcohol is dropped on the oil surface, there must have some other mechanism driving this. And so then from this regarding fragmentation, so like how fragmentation is actually qualified along with Rayleigh stability. And we think that Rayleigh stability describes a fluid by itself has like a fragmentation based on it wants to minimize its surface area. Therefore, this causes the fragmentation produced in the experiments. Therefore, we partially agree with the reporter in that Rayleigh stability is the main parameter that impacts the size of the fragments. However, there should be more investigation done regarding the speed and distance of the fragments. And so now moving on to Miss Physics, they talked about Rayleigh's plateau explanation, air bubbles created from the surface of the droplet expansion, as well as the wetting and de-wetting properties. And Miss Physics for some of the experimental parts are varying the impact angle, restricting droplets, multiple droplet interactions, such as restricting through containment.
Thank you. Okay, moving on to concluding remarks from the reporter.
Hi, sorry. So thank you to both the opponent and the reviewer for a very good discussion and review. And so with the opponent, I discussed using different fluids, such as hydrogen peroxide and the effect that would have on the phenomenon, as well as the fact that varying other parameters, such as temperature, would have on the phenomenon. I also just want to note on the reviewer's comment that with 100% alcohol, they did see fragmentation, because in my own experiments, I did not see that occur. So that was just something that interested me. But anyways, overall, I do believe I addressed the opponent's points that my theoretical and experimental results didn't quite match. And I addressed that by saying that most of my quantitative modeling was all proportional. And so because of that, there might have been some variation, although it was all in the same order of magnitude. And then, although I didn't investigate parameters that both the opponent and the reviewer mentioned, such as drop height and drop angle, I do believe I investigated the most important parameters to the experiment, which were the initial concentration of alcohol, the drop volume, and varying the type of oil. And so overall, I believe I was able to create a replicable and reliable experimental setup, as well as had very like time efficient method to actually quantify the number of droplets formed and the size of the droplets formed. And I believe that my theoretical modeling was robust and went beyond where the literature actually ended by considering like capillary pressure in the rim bulge and the plateau Rayleigh instability. And so again, thank you to both the reporter, no, sorry, that's me. Thank you to both the opponent and the reviewer, as well as to the jury for listening.
Thank you. Let's move on to jury questions, but just for the sake of time, let's actually time it to 5 minutes and get straight to grading. So feel free to ask questions.
Okay, I have a question for the reporter. You showed an image where you dropped like 99% alcohol, right?
No, I did not show an image. That was an image from a video.
Ah,
But
okay.
yes, that was.
So what was the
99%.
highest concentration that you tried?
I tried the highest concentration that I actually like measured the results for was 70% because, sorry, it was not 70, it was 50% because above that the droplets formed were too small to actually quantify using the image analysis software I used.
But you did try it, it's just that your software couldn't output any data.
Mhm.
Okay, all right, thank you.
No problem.
I can ask a question. So for the, I can ask first for the reporter, but anyone else can follow up on that. So you mentioned that like in terms of proportionalities, there's no correlation between initial volume and number of droplets. So what if we change the initial volume by changing the shape of, sorry, did you want to say something?
I did find a correlation between the volume and number of droplets. As you increase the initial volume, you get a lot more
But
droplets.
wasn't it gray in your picture?
So that was between initial concentration and the size of the droplets created.
Oh, okay. Okay, so I'll just my question. So what if you change the radius of the disk or the container to be the radius of the maximum mother droplet? Would you still see the effects? Like, would you still see the little fragmentation going on? And then other people can follow up.
Like just experimentally, when I did have a smaller, I started out using like a smaller container, and I did notice that it created a lot of droplets at the edges, but they were a lot smaller, and they stayed at the edge, if that makes sense.
I would like to follow up with that and say that I also saw a similar experience. Although one thing I did notice was the actual radius of the mother droplet stayed constant in that scenario, because I assumed that due to the edge effect of the small container, it prohibited the expansion and expansion of the mother droplet that we would otherwise see.
To the reviewer, when you did this experiment, did you try it? Because you did raise a couple of points for the reporter to try. Did you try, for example, with different colored food colorings?
Yes, we did try that.
Okay, were your food colorings still, what do you call this, water soluble, water based?
Yes, it is indeed water soluble and water based.
And what differences did you see between different colors other than visually, other than the color itself?
Other than the color itself, we didn't see any noticeable colorings because when we use like red or like different colors to depict like different concentrations of alcohol. So like we didn't like, or you didn't classify like color as like an as a quantitative parameter, because each of the different concentrations showed a different effect. So we mainly investigated the proportion between the water and alcohol having like, with the food color having negligible chemical effects.
Okay, I was just curious because each food coloring, you know, if you look at the ingredients, it's completely different other than the water.
Wait, sorry, I know it's a juror question period. I have a really quick comment. Did you add food coloring to the 100% alcohol? Because if the food coloring, if it's water-based, then it wouldn't really be 100% concentration anymore. Maybe that's why you got fragmentation.
No, actually, I partially agree with what you said. Like there will be no fragmentation of it actually occurring like at 100%. However, the mechanism is still there because all the parameters that you've listed or like that occur in the Maragoni effect are actually still present in the experiment, right? However, you just can't actually see a fragmentation because it is 100% concentrated, or it is 100% like concentration.
Any other questions?
I have one question for the reviewer. He mentioned the effect of height of dropping the droplet. I mean, did you try it itself? And what
Yes,
was
we
the
actually
maximum
tried to.
height?
Oh yeah, sorry. So we actually tried to drop a droplet from 2 meters. We didn't try to drop it from. We didn't find a reasonable maximum height. However, when we dropped it at 2 meters height, there was some loss of mass or loss of droplet size due to the air, of it going through the air. And this is largely, we just classified it as evaporation of the droplet. So based on this, it still proved to have a Mariani effect, because when it dropped into the oil, it almost reached the bottom, and as it resurfaces, it still creates the Mariani effect. However, it was just lesser than when we dropped it at a shorter distance, like the outer radius.
Thank you. So I think we should get to the scoring period now. Just like the previous round, message me in the chat when you're done scoring, and let's enter the scores. Okay, waiting on 2 more jurors. I think we're waiting on Ali Reza and Ahmed.
Ahmed just said he's ready.
Oh, okay, awesome. Ali Reza just messaged me. Okay, we can start. Okay, Neil, what are your report scores?
Reporter, I have leading 1 plus 6.5 plus 2.5 minus 0. And please tell me my math is right. That should be a 10.
Awesome. Shito?
Okay. Same, 6.5, 2.5, 0 for a total of 10.
Okay, Michael?
620 for a total of 9.
Thank you. Ahmed?
520 for a total of 8.
Okay, thank you. Itzel?
5.5, 2.50, total of 9.
Thank you. Dang?
630, total of 10.
Thank you. Daria had to leave, so I'm putting zeros as a placeholder for now. Jesse?
630 for total of 10.
Thank you. And Ali Reza? I know you messaged me, but let's have it announced so it's on the recording too.
Sure, no problem. 5.5, 2.5 minus 0.5, 8.5 total, but rounded to 9.
Perfect. Okay. For the opponent, Neil?
Sorry, I have leading 1 plus 1 plus 4 plus 3. That should get me a 9.
Okay,
right?
leading 1 plus 1 plus 4 plus 3 plus 0.
Plus minus 0 should get me a 9, right?
Perfect. Okay.
Yes.
Shito?
1330 Oh, sorry. Yeah, 1330. So that should give me a total of 8. Yeah.
Perfect. Michael?
2330 for a total of 9.
Thank you. Ahmed?
1.5, 3.5, 30.
Thank you. Total of 9, right?
Yes.
Okay. Itzel?
2, 3.25, 3.25, 0 for a total of 9.5.
Okay, which way are you rounding?
I round up.
Okay, so it's a 10. Okay, great. Dang?
1330, total of 8.
Thank you. Jesse?
2330, total of 9.
Thank you. Ali Reza?
2330, total 9.
Thank you. Okay, for the reviewer, Neil?
Leading 1 plus 2 plus 1 plus 2 plus 2 plus 0 minus 0 should give me 8.
Perfect. Sheetal?
So ignoring the leading one. 1, 2, 2, 2, 0, 0. Total of 8. Perfect.
Perfect. Michael?
2, 2, 2, 1, 0, minus 1.
Thank you. Ahmed?
1.5, 2, 2, 1.5, 0.5, 0. I think that's 8.5 at the end.
Okay. Which way are you rounding?
Up.
Up, okay. Oh, sorry. 1.5. So it's a 9 at the end, right?
Yeah.
Okay, thank you. Itzel?
2 plus 2.5 plus 2 plus 1.5 plus 0 minus 0, which is 9.
Thank you. Perfect. Dang?
2, 2, 2. 1 minus 1, 0. 7.
Perfect. Jesse?
123,110, total 9.
Sorry, okay. Is the first one the leading one?
It shouldn't be. I'm just reading the ones that I put in. There's
Okay.
6 numbers, right?
Okay, yeah. So 1, 2, 3.
110 for a total of 9.
Perfect. Thank you. And Ali Reza?
2322, total 10.
Perfect. Okay, so let's just have one person quickly comment. I'll pick the lowest grade quickly. Ahmed, can you comment on the reporter?
Yeah, I thought it was a good report overall. I just would have liked to see more of a quantitative description of the deviations from the experiment.
Thank you. Dang, can you comment on the opponent?
I think they raised some good points, but I think they misunderstood the importance of the proportionalities and the implications that the reporter has found.
Perfect. Thank you. And Michael, can you comment on the reviewer?
Oh, I was just a little suspicious about the evaporation during falling. I thought they could have explained that a bit more, and also the drop angle, what they meant by that.
Okay, perfect. Thank you. I will submit these. It's 6:41. Let's take a 4-minute break and start the next stage at 6:45. Thank you.
How about this? Let's just get the final team to go into their prep time, and then when the prep time
sure.
is done,
Perfect.
we could just start. So for anyone that's not on that team, you can take a 5-minute break.
So who is reporting from VP?
Roshan Yen.
Perfect. And who's the opponent from Short Shield? Or Short Children?
Jing Yuan Sun.
Perfect. And who's the reviewer from UTS? Sorry, who?
Emily.
Oh, Emily. Okay, perfect. Okay. Yeah, let's start the reporter's prep.
I think I should just briefly talk about what we're going to do with Daria's score. Since she scored for the first round, her score will be kept. And then for the second and third round, because it's incomplete and she's not here, we're going to compute all the other jurors' score according to the rules, which is, highest and lowest average, and then average with all the other ones. And then we will put the final average score as Daria's score. So it wouldn't, affect the final score that you guys get. Okay. Dave, we're gonna do that, right?
Am I doing that?
Well, we'll do that together when we verify it, right? Yeah.
Perfect. Yeah, that sounds like a good plan. Okay.
So we have about 30 seconds left. I just want to confirm if all of the jurors are back and maybe the other teams as well. if most of us are back, then we can start right on time. And I'll let Dave take some rest from speaking. And he will have to like verify the score. So I'll do the speaking. So reporter, ready? Let's begin.
Hello, my name is Roshan Yen, and I am the reporter for Victoria Park Collegiate Institute. The problem I will be presenting is problem G, equipotential lines. And the problem statement is, place 2 electrodes into water, supply a safe voltage, and use a voltmeter to determine electric potential at various locations. Investigate how the measured equipotential lines deviate from your expectations for different conditions in liquids. The interesting part I found about this problem is that there's multiple ways to interpret the 2 electrodes part. Unfortunately, we weren't able to test all the possibilities because our power supply was partially broken. But one way you could have interpreted it is that you could, it depends on the potential of the electrodes. You could either have one at what is effectively 0 volts and the other one at your positive voltage, or you could have one positive and one negative and then have like the middle, like ground voltage to probe off of. So, and the parameters we measured were voltage, conductivity of fluid, voltage distribution, and ion concentration. So the overview of the presentation is first the introduction, then the experimental setup, then the theoretical model, and the key parameter interaction, and the conclusion. So the experimental setup. For the experimental setup, we had a container of tap water with 2 copper rods in it, and we used power supply and a multimeter to provide the power and use measurements, and we recorded it with a phone on a tripod. Here's another view of the diagram of the bucket. We had to have a grounding wire because otherwise static charges would build up in the water and we wouldn't get any useful information. Here are 2 photos with labels. So you see the 2 positive electrodes here and here, and you have the power supply there. The measurement method we used was a multimeter, which we used voltmeter, that function that's built in, which was plus or minus 0.001 volts. The experiment, the points we measured with these points, each are labeled, and then there will be graphs later in the presentation. The theoretical model. So the first theoretical model, I'll be showing the geometry. So this is sort of a diagram of the bucket with 2 electrodes in it, and these are these electric field lines. The important part here is that in the middle, because the same charges repel, you have these diverging electric field lines. Whereas on the outside, it's more or less similar to if you only had 1 electrode. So you can calculate the voltage potential by multiplying it by kq over r, where k is Coulomb's constant, q is your charge, and r is the distance. Now, another equation that we found was interesting, but we didn't end up using it for a theoretical model, was E equals minus delta phi over d. This is the calculating the electric field in between 2 different electric potentials. We didn't end up using this, but it was interesting to see how it worked, and it provided some useful insight. So this is the combined solution. Here, this is you have the 2 electrodes, and these are the equipotential lines. Now, they don't exactly match up to our experimental model because this is very much a theoretical model, and it's not very applicable to the real world because you have these 2 points, and as you get closer and closer to them, the voltage goes to infinity. This is how it would work in theory. Like, it does make sense, but it's not very applicable because you can't have infinite voltage in real life. Now, some assumptions we made was that the experiment done with tap water was very close to ideal conditions, and lingering static charges are not present, and that electricity will always take the shortest path. This will be important later. So this is the experimental verification. Here you have the blue is the experimental data, and the for each point in the diagram. So each number here down here is the corresponds to a point in the diagram I showed earlier with the different points labeled. So the conductivity. We've used three total different solutions of water and salt water. So the conductivity is, the total conductivity of water is not that much, so we didn't calculate that. But when you add salt, it becomes more conductive, and this is how we calculated it. And the effect of it is that when you have higher conductivity, the electricity, the power is able to travel further, and so the equipotential lines are sort of pushed outwards. Here is data. So the voltage was overall higher with the more salt, so it would be more conductive, and this shows that the equipotential lines would be pushed outwards because there's less resistance. Okay, I need to go back to explain I think that slide got deleted. But so yeah, the thing I was talking about with the tap water being assumed to be ideal was that it wasn't feasible to collect enough information during the experiment to be able to find Q. So what we ended up having to do is derive Q from the experimental data, where so KQ was equal to V plus R1 in V times R1 in brackets plus V plus R2 in brackets, and then we divide that by 2 because we're adding the total potential between the two electrodes and then dividing them by 2 to average them. So we get the equivalent potential. And then from that we can get the charge. So the key parameters we varied were conductivity, ion concentration, and distance. So conductivity and ion concentration resulted in a negative correlation for the spread of voltage and the voltage value, while the distance resulted in a positive correlation and wasn't very comparable to the spread of voltage. So in conclusion, the problem statement was place 2 electrodes into water, supply a safe voltage, and use a voltmeter to determine electric potential at various locations. Investigate how the measured equipotential lines deviate from your expectations for different conditions and liquids. We were able to analyze the parameters of conductivity, ion concentration to see its effects on voltage distribution and intensity of voltage at a specific point. Here are references. Thank you for listening.
All right, so let's go on to the next stage. That's for the question from the opponents.
Okay, thank you for your presentation. I have a few questions. So first question is, do you think the radius of the cylinder, like cylindrical anodes and cathodes that you use matter?
No, because so electricity takes the path of least resistance. And so if the liquid is a solution, it should be equally conductive in all directions. So the path of least resistance will also be the shortest path. So you can just subtract the radius of the electrode from your distance, and then that will, because you can sort of imagine the.
Okay, thank you. Okay,
like a giant circle of points, right?
Okay, thank you. Okay, my second question is, why are there 2 positive terminals in your graph? Because the 2-point charges that you're assuming are both positive.
Yes, we thought it would be interesting to investigate the sort of having 2 electrodes because you get the 2 charges in the middle that are interacting.
Okay, thank you. My third question is, in one of your theoretical model, you said that you use tap water, and then you mentioned that tap water is ideal, and then you go on to talk about how adding ion will actually affect the conductivity of the fluid. So why do you do you still think using tap water is an ideal assumption to make?
We had to assume it's ideal. Okay, so another investigation we did was with just the test was with oil. because oil is not conductive at all. Because the experiment works worse when the liquid is more conductive, but it also doesn't work at all if it's not conductive. So
Okay.
you have to sort of tread this fine line.
Okay, thank you. Moving on to my next question, what do you think is the most important parameter that you talked about in your presentation?
The most important parameter I talked about in my presentation was probably the liquid.
All right, I believe we are out of time,
Okay,
so let's
thank
go
you.
on to the next stage. 3 minutes of preparation by the opponent.
I think the reporter has to stop share.
Yes, indeed. So opponent, put your slides up and we will begin.
Okay, can you see my slides?
Yep.
Okay, I'll begin now. So hi everyone, my name is Oscar and today I'll be opposing problem G equipotential lines. Let's revisit the problem statement. Place 2 electrodes into water, supply a safe voltage and use a voltmeter to determine electric potential at various locations. Investigate how the measured equipotential lines deviate from your expectations for different conditions and liquids. So some tasks that we determine for this phenomenon or for this problem is, first of all, the presenter needs to determine the electric potential at different points in the liquid using a voltmeter. And second of all, investigate the deviation between experiments and theory, as that is stated in the problem statement. The third task will be to vary experimental setup to investigate the phenomenon for different conditions, for example, different fluids, which is task number 4, investigate the phenomenon for different types of fluids, as well as some other different parameters. For example, like the size of the cathode or so on. Okay, so this is a summary of the report. So in the presentation, the presenter demonstrated a partial fulfillment of this problem because they have a limited experimental scope and there are still some improvements possible for their theoretical model. In their theoretical analysis, they first of all talk about, they gave equations for the charge at a point, and then they provide a combined solution matching voltage. And lastly, they talk about how adding ions to change conductivity will alter the phenomenon or alter the equipotential lines. In their experimental confirmation, they presented a reducible setup. They measure the voltage using a multimeter, and they demonstrate how they measure the volt at different locations using grid lines. So some merits and next steps. So first of all, the presenter talked about electric potential of point charge and assume cathodes are point charges. The presenter is able to demonstrate a preliminary experimental setup and map potential based on a few points taken by the voltmeter. And last but not least, the presenter demonstrated a simple conductivity analysis by adding ions to tap water. So here are some possible next steps for the presenter. First of all, the presenter can maybe like explain qualitatively why the equipotential lines are the way they are shaped for this phenomenon. And then they can talk about how they are able to match their model, how they're able to match their theoretical model with experimental verification, because in a presentation, there's not enough information about their theoretical model, and there's no matching or mapping between the theoretical model and experimental data. And then the presenter can improve their experiments by, for example, adding more points for more exact characterization. And yeah. And the fourth point is that they can investigate different types of liquid, for example, glycerol, dish soap, and milk. I am under the impression that the reporter only uses a tap water and adds some ions into the tap water. And number five, the reporter should investigate more parameters such as temperature, density, and dynamic viscosity of the fluid. So, so here is an overview of my discussion. I'll be discussing how an improved experimental setup is achievable, and I'll be talking about the difference between polarization, polar and ionic molecules, and then we'll talk about whether or not it's possible to predict the shape of the equipotential lines theoretically, and then we'll talk about the relevant parameter interactions and error analysis. So with that, I invite the reporter to join me in the discussion. Thank you. Sorry, can you start sharing your slide again? I just want to yeah. I just want to go over your slide.
There you go. Now, which slide do you want?
Can you just exit the presenting mode, and then we can go through your slide from the beginning?
Okay.
Okay. Can you go down? Can you go to your experimental setup?
This one here.
Okay, can you scroll up a little bit? Okay, doesn't matter. I saw from our presentation, you actually use cylindrical cathodes and anodes. And the way you connect the cathodes and anodes with the in the circuit is you actually put the alligator clip into the cathode and anode. Do you think that's it's enough to connect the circuits? Because I think it's not in direct contact, right? You just put the alligator clips into the cylindrical structure. Is that what you did?
Before each run, I would measure the voltage of the power supply with the multimeter on the cathode and anode. It worked perfectly fine.
But did you put the alligator clip into the cylinder?
So you have the hollow cylinder, I clipped it onto the wall.
Okay, makes sense. Can you just move on? Just scroll down, and not scroll down, but move on to the next slide so we can just see each slide, every slide. Okay, please move on. Okay, for experimental measurement, I see you're using a grid line, right? Do you think that's accurate enough for you to just get some data and then get the prediction of the equipotential line? Or do you think okay, continue please. Okay, I'll just finish my question. So in your experimental setup, you use grid lines, right? Do you think the points that you collect are very discrete and they do not represent a continuous curve because equipotential is a curve, right? So if you can improve your experimental setup, how would you go about like collecting continuous data?
Yeah,
of
well, we
the
thought I had
equipotential?
Yeah, okay.
Sorry?
Are you done with your question? No, not the answer. Sorry.
Sorry, can you go back to slide number 9? And also, I didn't hear what you were talking. Okay, yeah, this slide.
Yes. So, as you were asking, how would I have improved it? Yeah. So one thought I was having as I was finishing this presentation was that rather than measuring it by hand, what I could have done is have like, because if there's just a piece of metal in the water that's not connected to anything, it doesn't really affect the experiment at all, like that much. So what I could have had is a bunch of pins, and then use relays to choose which pin we're probing off of at the moment, and then you could control that using, say, an Arduino, and measure off like 1,000 points per run rather than just like 13 points.
Yeah,
So
I
you could
think
have
that's like,
smaller increments.
yeah, I think that could be a valid experimental setup. So what I thought about this problem is like instead of like manually just like putting the probe and like each point on the grid line, we can just like design something that will actually like the mechanical device will actually like move the thing in the container, and then like by moving it like in the container, you can actually see the voltage change, and then like so that way like the data is like more continuous rather than being like just like discrete points like 100 points on the grid paper. So that's like not enough to. It doesn't have like enough predictive power, right? So yeah, I'm glad we reached an agreement on that point. Can you go on to your theoretical model? Slide number 12. Can you tell me why you assume 2 positive electrodes in your theoretical model?
Because that's what we use for the experimental model, and we wanted the theoretical model to compare our experimental data to.
Yeah, but like you're connecting the 2 electrodes in like a circuit, right? So there must be a negative terminal and a positive terminal, right? So are your charges like the plus or minus charges correct that you're like assuming here?
Yeah, let me go back to the experimental. They're both electrodes. Well, this is an old photo, but we changed it after. Both the electrodes are connected to the same, both have the same voltage, and then there is a grounding pin in the water, because one issue we found while setting up the experiment is that if you just have a positive electrode in it, static charges will build up in the water. So you need some way for the static charges to dissipate. So we had to add a grounding pin into the liquid.
Okay, so what would your equipotential line look like if, let's assume there is 1 plus charge and 1 negative charge in your diagram? Do they like look different?
Look different.
Equipotential lines.
Yeah, here, let me go to the diagram. So this is with 2, they would look different. Here, let me just go pull up MS Paint real quick. Draw it. I think it would look somewhat like, let me draw the electric field lines, because, so if you have 1 positive and 1 negative, you'd have the like electric field lines somewhat like this.
Sorry, I'm now seeing you. Okay. I opened up my Zoom. Can you are you demonstrating like using hands or something?
Maybe I'm not sharing the entire screen.
No, you are sharing it. Okay.
Can you see you can see the MS Paint window, right?
Yeah, I can see it. Okay. I got what you're saying.
Then like the equipotential lines would look something like this.
Then I'm not seeing your screen unless you're doing something. You're still on your presentation.
Oh.
Are you drawing something?
Yeah.
Okay.
Here, so the red is the electric field lines, and then the darker thing is the equipotential lines. It looks something like this, with sort of line in between them where there is 0.
Okay, thank you. I think we can move on to the next questions. Can you go to slide number 17?
Yes.
Yeah. So my first question is, why do you use a bar graph for this? Is it because like your data is not continuous and that's why you use a bar graph? And what is like the position? Because the position in your grid line is like a 2D thing, right? Because you have like X direction and Y direction. So are you like collecting the data along the axis or along the line the cathodes and anodes are on, the electrodes are on?
So the reason why you chose the bar graph is because we felt it's the best way, because our data is not really like continuous. We felt it's the best way to represent it, and the position recorded refers back to the points here. So you have 0.1, 0.2, 0.3, etc.
Oh, okay, I see that. Okay, I see it. Okay, thank you. Thank you. I think we can move on. Can you go to your conductivity model?
Connectivity, this one?
Yeah. Okay, so for your assumption for conductivity, you assume like tap water is ideal, right? Do you think like just like distilled water will work in your experiment? Why or why not?
I think distilled water would work because even though so one thing we observed was that there was either no current or very, very small current flowing through it. So while distilled water is practically non-conductive, it is still polar, so it would probably still work. We didn't have any distilled water to try with though.
Yeah, I partially agree. So first of all, I think like distilled water would, I disagree because I think distilled water will have the same like results experimentally and demonstrate the phenomenon because water is actually polar and water is conductive. Water is conductive. And but I agree with you is because like the thing is like water molecule is polar, right? So this thing should still work with water. It's just that with like the tap water and ions, I think there's gonna be like a movement of ions, not only just like the electrons in your like circuit. So that might like mess up your theoretical model a little bit. So yeah, but I think we can move on to your next few slides. Can you scroll down a bit? Okay, let's go to key parameters. Okay, do you think different types of fluid is an important parameter for this problem?
The different types of fluid is included, is part of the ion concentration and conductivity.
For example, I have milk and water.
Yeah, I mean, so like you can sort of imagine milk as water with a bunch of ions in it, because it's just water with a lot of impurities, right?
Okay, so you're saying whether or not this problem will work depend on whether or not there's ions dissolved in the solution. I disagree because I think I think that this problem is able to work as long as the liquid is polar. There doesn't need to be like there doesn't need to be the ions in the fluid because the polarity will actually react to the like if there's current passing through the medium, the polarity will react to the current and then they will like orient in a certain way that aligns with the potential line. But yeah, thank you. I think that's the end of our discussion. Thank you.
We are out of time. Thank you for the awesome discussion.
Thank you.
1 minute to summarize.
I really enjoyed this discussion with the with the presenter. And I thank the jurors for listening to our discussion. In our discussion, first of all, we talk about how an improved experimental setup is possible. I suggest using some kind of mechanical devices to track the voltage on a continuous curve rather than using grid lines to track like each individual points. And then we move on to talk about the difference between polar and ionic molecules. And I disagree with the presenter because I think with polar molecules, this phenomenon is able to happen. And then we talk about the relevant parameter interactions such as different fluids, etc. And we also look a little bit into his experimental setup, including how the two like electrodes are cylindrical and whether or not the radius of the cylinder will affect this phenomenon, why he assumes the two electrodes are positively charged, and how the equipotential line will look like if the two electrodes are oppositely charged. But yeah, thank you so much for listening to answering my questions and listening to my discussion. Thank you.
Cool. And now let's go to the next stage, which is the question by the reviewer.
Can I begin? Okay, so I think that was a very interesting discussion. I have a few questions for the reporter first. How would you think different metals would affect the results seen of equipotential lines, both in qualitatively as in like shape and quantitatively as in magnitude.
So different metals as in like the metal for the electrode, right?
Yeah.
Yeah, I think one difference it would make is that we'd get some sort of galvanic corrosion as well as like electroplating occurring, which is one issue we had because while both like the electrodes we were charging were copper, the grounding wire we were using was an aluminum alligator clip, and we ended up having some copper getting plated onto the alligator clip.
Thank you. And for the opponent, what would you say would be the most important parameter?
The most important parameter, I think this probably is like different kind of fluids because whether or not the fluid is polar or non-polar will directly determine whether or not this experiment will happen. For example, using oil, which is non-polar, this experiment will not happen at all. But using water, not like tap water, even distilled water, because it is polar, this phenomenon will happen. So it's the polarity of the molecules that determine whether or not this phenomenon will happen.
And for the reporter, I know you didn't get a chance to test with different plates, but how do you think the equipotential lines would vary with, for example, instead of using 2 point electrodes, using, for example, plates or rod or a horizontal rod?
Well, horizontal rod would here. Can I draw I'll draw a diagram.
Or well, the question was more of like, do you think this would impact the equipotential lines?
Well, it would change the shape, but they would still work regardless.
What about the magnitude?
The magnitude, I don't think it would, like, provided like everything else remains the same, I don't think it would change the magnitude.
And for the opponent, do you agree with the reporter?
I think different dimensions or different types of electrodes used would just like affect the theoretical model a little bit, but like overall the shape or direction of the equipotentialism would be the same. From my own experience, it would just be like doing like more complicated math, like with like different dimensions of the electrodes. That's the only difference.
So you're saying that if you had, for example, 2 plates, the shape of the equipotential lines would still be the same as if you had 2 points?
Short answer, please.
Reporter? The shape would be different.
Oh, this is for the opponent, since they mentioned that shape should be
Yeah, the shape will be different. Like the direction will be the same, but like based on like different like math, the prediction of different the prediction of equipotential, the shape of equipotential lines using like different dimensions of electrodes will be different. Sorry if I like mispronounced that.
Next stage, which I believe it is the preparation of the reviewer.
Hello, can the reporter please stop sharing?
So let's go on to the next page. Viewer, please begin your speech.
Hi, I'm Emily X from UTS, and I will be reviewing problem number G, equipotential lines. So the problem states that place two electrodes in water supply a safe voltage and use a voltmeter to determine electric potential at various locations. Investigate how measured equipotential lines deviate from your expectations for different conditions in liquids. So I believe that the tasks that are important to actually solving this problem would be to create a successful, repeatable experimental setup, to quantitatively and qualitatively explain the phenomenon, create a successful theory examining the equipotential at various positions and explaining the shape of the equipotential lines, and lastly, isolate and test for important parameters, including input voltage, liquid properties, metal materials, and dimensions of the electrode, and experimentally verify how these parameters would affect the phenomenon. So a summary of the report, I believe that the reporter had a partial fulfillment for the understanding of the problem. There are experimental and theoretical extensions that are possible. For theoretical analysis, the reporter analyzed equipotential zones and conduction variation, and for experimental confirmation, they examined graphing potential lines, electric potential measurements, and conductivity. So for merits and next steps for the reporter, they could potentially improve their, although they did have a successful experimental setup, possible next steps would be to place electrodes at various locations, including further from the either end of the box that they use, because then there would be edge effects and also potentially charge buildup on the surface of the box. And they were able to graph equipotential lines only using their theoretical model. For possible next steps, they could use their experimental data to graph actual equipotential lines. And lastly, they did vary some key parameters, specifically the properties of liquid by adding salt. But I think some possible next steps would be to investigate other parameters, including the shapes of electrodes, conductivity of liquids, and distance between electrodes. Additionally, they can improve their scientific communication, since the bar graph would not be the best way to represent such a problem. So for the opposition, they brought up 3 key points, which was to improve the experimental setup, add a theoretical prediction of equipotential lines, and to vary more parameters and predict the effects. I think for the opponent, their merits were that they were able to summarize the reporter presentation well and identified the merits and flaws of the presentation. However, for possible next steps, they did not address how to graph equipotential lines from experimental data, and did not probe the reporter to explain deviations between experimental and theoretical, and did not examine alternative probe structure. So for our first discussional analysis, the opponent raised a point where they suggested the reporter to manually probe at various points to collect continuous data on equipotential lines. And the reporter responded that yes, this would improve their experimental data collected. But I partially agree with this point, because they, although manually probing along a grid would give better data, it takes a lot of time, and graphing the equipotential lines directly from collected data is not very accurate. So I would recommend in the future to use Python and Matplot to extrapolate using the data that they collected to actually graph the equipotential lines. And for the second point, the opponent raised a point about representation of data in bar graph, and the reporter's response was that bar graph was the best way to represent the data. I disagree with the reporter, because bar graphs are almost never the best way to represent continuous quantitative data. I think that using a line graph or 3D plot based on the position of the reported measurements would be a lot better, and deviations were not successfully analyzed by either the opponent or the reporter. And lastly, for the fluid types, the opponent raised the points where fluid types don't matter and the liquid needs to be polar, and the reporter responded with that there must be ions in the fluid for the phenomenon to work. I agree with the opponent that different types of fluid would impact the equipotential lines measured, but I disagree with the reporter that there must be ions in the fluid for the phenomenon to work, because I used deionized water and was still able to graph equipotential lines. And lastly, for missed physics,
I believe we are out of time. So let's go to the next stage. Concluding remarks by the reporter.
So in my presentation, I presented our theoretical and experimental data, and how we managed to show how the models somewhat match and how our theoretical model works. Now, for the discussion portion, I mostly agree with the opposition, what we discussed, how the experiment could be improved. Now, I think there was a misunderstanding in between the report, the opposition, and the reviewer, in that they think that I said that there must be ions in the fluid. What I was saying was, with this point that maybe milk could work. What I was saying is that milk can be thought of as water with ions in it. And my point with what must be needed to work was that the fluid must be polar, because non-polar fluids do not work as we experiment with oil. So yeah, largely I'm in agreement with, I largely agree with the reporter. We disagreed on a few points, but I don't think they're that important. They're probably more to do with communication than actual disagreements. The reviewer had a few interesting points. Now, so one of the points brought up by the reviewer was that it would be better to interpolate using Python or Matplotlib. But one of the ideas I had suggested during my discussion with the opposition was that we could just use more probes using either using a mechanical method or by just physically having more probes, which I feel would be better because you're actually getting more data rather than extrapolating it from what you already got, what little data you already have. So yeah, in conclusion, we had a very good, fruitful discussion with the opposition in review. So yeah, that concludes it.
Right, thank you. So we will move on to the next stage, which is juror questions.
Okay, I have one question for the reporter. In your page 21 and page 9, I want you to compare this too, because in your experimental verification, your position 11 is the closest to one of the positive points, positive nodes, but you still get a very low potential for the blue, when you added conductivity. I mean, can you explain if this point of data is reliable, and if you repeated that experiment a couple of times to make sure that this point is reliable?
Yeah, we did multiple runs, so we did 3 for each different type of fluid we did. So I do think that the information, the data is reliable. I have a few ideas on why it was an outlier. So I think it has to do with the grounding pin, because it's to deal with the issue of the liquid developing a static charge over time. Now, what I think is going on is because point 11, so point 3 and point 11 are pretty much equivalent in terms of what their potential should be. However, the main difference is that point 11 is closer to the grounding pin. So it might be more, so there might be less static charges in the liquid where point 11 is. Because
did you try to move around the ground and see if this confirms your hypothesis?
Didn't have the opportunity to do that, unfortunately.
Okay, thank you.
Hi, also for the reporter, thank you for that. In your correlations or your correlation slide, if you could bring it up, the ones with the yellow and blue lines, the one that show this one's a positive correlation or positive influence. Okay, you have here distance is positively correlated with voltage value. Does that mean the farther I am, the higher the voltage value?
The closer you are, the higher the voltage.
Yeah, okay, then that should be a blue line, right?
Yeah, I guess.
Oh yes, because positive means one bigger, the other should be bigger.
Yes.
Okay, so that should be a blue line. Okay. I don't have further questions.
I have one question for the opponent. He mentioned that if the experimenter, the reporter, can actually get some continuous data. I was wondering if they tried it and if they got any continuous data, and what was the comparison with the theory?
Yeah, we actually did try to build a setup where there's like a there's like a mechanical device that will like move the probe in water and sort of, and then we'll just like read the change in voltmeter. And then like and then we try to get like as many points as possible and just like not only depend on like the grid lines. So we're able to get some continuous data and they experimentally like match with our prediction. The only problem is like without doing the theory beforehand and without knowing the shape of like the equipotential line, like the probe, like the probe that's like testing the voltage might like cross some potential lines. So there's going to be change. Like we can't just like trace out the the shape of the equipotential line. Like sometimes we might cross and there's like a lot of like data points for us to like just like look at. Yeah, but we did try. And I think the result is satisfactory.
So you call that one is still a continuous data because you're still collecting data points and not a continuous really.
Yeah, but that, okay, I think that's like a more continuous approach than just like putting the grid lines like like into just like putting like discrete points into the grid line. There's definitely like improvements possible with if the computer can read like the voltage different points if there's like a computer setup or like a computer program. Yeah.
Okay, I agree with that one. But another one, you mentioned different liquids to be used. Do we still have time? Did you use any different liquids and did you get anything interesting out of it?
We used oil. Oil is non-polar, so the phenomenon does not happen. And then we actually created something interesting because we put oil on like above water, and we try to see like how that will like it's kind of interesting. Like when I put the probe into the oil, there's like no like voltage created in the circuit at all. But then as soon as I touch like water, the interface between the oil and water, there's like the electric field created. We also tested using like milk, but we also tested like using milk, but like it returns similar results compared with water.
All right. So any other jurors have any questions?
Yes, I have a question.
Okay.
For Oscar. Just a quick question. Okay, so you said that like this experiment could work with any polar liquid. Do polar liquids, like, can you send a current through a polar liquid?
Sorry, yes.
I see. Okay, thank you.
I had one in case it's not too much of an inconvenience.
Please go ahead.
Yeah.
Go ahead.
I have a question for the reviewer. So I was really impressed by this, that the reviewer actually tried to use deionized water. So I'm just curious, what did you get with deionized water in one sentence? And in one sentence, how is it different from distilled water?
I wasn't able to use distilled water, which is why I used deionized water. And I found that the lines actually, I mainly measured between two parallel plates. That was the best, like, I guess, a potential line graph I could plot. But it wasn't as consistent as using, for example, tap water, because deionized water, when there's like less ions, it's harder for us like strong electric potential lines to form. Yeah.
Okay, thank you so much.
Right, I think we are running a little bit late in terms of time. So jurors, if you have your score ready, you can just announce it, I guess. Dave, you can.
Sure, we can do that. Yeah.
Mm-hmm. Go ahead.
Or do you want me to go through everyone right now, or I don't think everyone's done yet. That's why.
I'm done.
Okay, fine. We'll just go. Whoever is done, just let me know, and I'll go person by person instead. So Neil, just let me know all your scores.
Okay, for the reporter, I have 1 + 5 + 2 - 0 for a total of 8.
Okay, thank you. And for opponent?
Opponent, I have leading 1 + 2 + 3 + 4. Yeah, that's a 10. And for the reviewer, I have leading 1 + 2 + 2 + 2 + 1. That should give me an 8.
Okay.
I believe Jesse.
Ali Reza.
Go
okay.
ahead.
Well, yeah, Ali Reza, you wanna give me yours?
For the reporter, 3.5, 1.5, and 0. That's a 6. For the opponent, 1, 3, 3.5, and 0. That's 8.5. You can round it to 9. It's fine. And then for the reviewer, 1, 2, 2, 1, 0, and 0. So it would be a 7.
Yep, Jesse.
Yeah, okay, so for the reporter, I have 520 for a total of 8. The opponent, 233 and 0 for a total of 9. The reviewer, 1322 plus 1 minus 0 for a total of 10.
1, 3, 2, 2.
1, 3,
and
2,
0,
2,
0.
1, 0 for 10. Yeah.
Oh, wait, sorry. Can you say the review one a bit slower?
1, 3, 2, 2, 1, 0 for a total of 10.
Thank you. Okay, and then Shito?
Okay, so for the reporter, I have 510. So that should be 7.
Okay.
For the opponent, I have 1, 2, 3, 0. So should also be 7. And for the reviewer, I have 2, 3, 3, 1, 0, 0. So that should be 10. Yeah. Thanks.
Thank you. Dang?
For the reporter, I have 310 for a total of 5.
Okay.
For the opponent, I have 133 minus 1 for a total of 7.
Okay.
And then for the reviewer, I have 133 1 0 0 for a total of 9.
Thank you. Michael?
For the reporter, I have 410 for a total of 6.
Thank you.
Opponent is 1331 for a total of 7.
Okay.
And then reviewer is 222100 for a total of 8.
Thank you. Ahmed?
For the reporter, I have 420 for a total of 7.
Okay.
For the opponent, I have 232.5, which rounds up to 8. For the reviewer,
Wait, sorry. For the opponent, you have 232.50.
yes.
That's an 8.5, but then you said rounds up to 8.
Oh, sorry. I guess it rounds up to 9 then.
Okay. Cool. Thank you.
And for the reviewer, I have 1.5, 2.5, 2, 1.500, which rounds up to 9. I believe.
Thank you. Itzel?
For the reporter, I have a score of 4.5 plus 2.5 minus 0 for a total of 8.
Thank you.
For the opponent, it's 2 plus 3.5 plus 3 minus 0 for a total of 9.5. I round it to 10. For the reviewer, it's 2 plus 2.5 plus 2.5 plus 1.5 plus 0 minus 0 for a total of 9.5, and I round that to 10.
Thank you. And is that everyone? I think that's everyone. Okay. Let's put placeholders for Dario. Perfect. For comments, I think the lowest score was by you, Dang. Do you want to briefly comment on the report?
Yeah, I thought that the report was limited in both experimental setup and theoretical, I guess, work. And I agree with both the reviewer and the opponent that the bar graph was not a very particularly informative form of communication.
Thank you. Shito, you gave one of the lowest marks for opponent.
In the discussion, I felt as though the opponent was focusing on a lot on what's missing, and some suggestions for improvement were not really there. So I was hoping it would be more productive to be constructive rather than deconstructive.
Thank you. And Alireza, you give the lowest score for reviewer.
I guess reviewer could have actually see some of the errors and missings in the report a little more, since she was listening to both of them. So, but in general, it was fine.
Thank you. So we're done all 3 rounds now. Jim, you can take it from here.
So like it's great. We've done all 3 rounds. So like everyone has worked super hard to reach this point. So Dave and I will just leave you guys in this room with Ryan and Andrew here for a moment. We will go and validate the scores, and then we will come back with the rankings, and then we will go to our award ceremony. And also our 2 guest speakers for today are also here, Professor Bailey and Dr. Nokovic. They're already like in the call, so maybe you can just give them like a welcome clap emoji or something. Yeah, we will go look at the scores. Okay, yeah, we'll be right back.
Hi, everyone. Just a reminder to all the jurors, please upload your score sheets like right now if you haven't already. We're literally validating the scores right now. Thank you.
Hi, everyone. Thank you. It's been a good 2 weeks. I'm sure there's a lot of sleepless night for all of you guys. Most of you guys probably didn't sleep last night and this morning. So we are done, and give yourself a pat on the back. It is great to see all of you here. And while Jim and Dave is tallying the actual result, we should have the results soon. Now, I would like to say one thing. Thank you all for joining in and participating in this event. Without you guys being participants, this event wouldn't work. And then I would like to also talk about another thing is we do give out financial aids and actually help. So for example, Dave was on our Discord server last night. This morning, he also didn't really sleep. Lots of you guys were asking for help, right? And we're giving out, he was helping out you guys one at a time. And we also gave out financial aids, as in if you cannot find, for example, sponsors or anything like that, because to do experiment, it does cost a little, well, it actually costs money. So therefore, if you are in need of financial aids, please do contact us. Okay, please do contact CaYPT at stemfellowship.ca. We will see what we can do. This year we have gave out a few financial aids to different teams. The result was actually great. Now, for the financial aid, the things that you purchase, we don't ask you to give it back. Like, you don't have to mail it back to us. We will ask you to put it into your day school, okay, to help your day school's physics lab to actually increase some of their inventory, and then hopefully this tradition can pass on to the next generation, or the next year, right? So if you are interested, and then please feel free to contact us. You can simply just leave the equipment there. So if you bought like adrenals or step motors, those can be used the year after. for us, our equipment, we have collected them over the past 5-6 years. We didn't buy everything all in one shot. It is every year we improve. So every year, if you can, if you want to, if this tradition can be passed on, then definitely the experimental parts can get a lot better. And we have Dr. Nukovic and Dr. Bailey here. So they're ready to give out awards in a bit. We're just still waiting. Thank you very much. And without their support, this is also not possible. Again, thank you, Dr. Bailey and Dr. Nukovic. So for now, we'll just wait a bit. Hey, Jim is back.
Sorry to interrupt. I just want to see if Andrew's here. Dave and I are running into some problems with the validation. We can't find some buttons, so we need Andrew.
Okay.
Join the committee Discord call, please. Thank you.
So if that's the case, then we will take a short break. I will play some music. Okay, and we'll be back. We'll be back. Let me find some relaxing music. sorry to stop this relaxing music. Sorry. There's one thing I forgot to say. For the national selections, for the actual national selection for the training camp, we would like all of you guys to actually submit your slides. Okay, and your team member, we will contact Jim will contact you guys, and then we will do this afterwards. You actually can after today, you guys you still have a lot of time to actually work on your presentations. The actual submission deadline for the individual report, it is not until end of March, if I remember correctly. So if you want to continue to work on it, improve on it, okay, have a shot at the national camp and the Team Canada, then please do submit. All of you guys get a chance. Okay, everybody is the same, but the chances for everybody are the same. So please do submit your reports, and there will be a guideline, and then they will be based on team. So for example, I believe every year there is a team evaluations and how much every member has put in, and based on percentage and things like that, we have a different marking criteria. Okay, and then we will look at everybody's report. So please do submit, everybody. I have seen so many of it today that it's actually very, very good. So, and some of you are first time participating, and some of the first time participant, your report literally made me, I was very surprised. Okay, I was very surprised at how well done it is. So please do submit. All right, thank you very much. I think that's all. Thank you. Let's go back to that very relaxing music. this. So the technical difficulty is still there, and our IT head is having a Wi-Fi problem, so he's restarting his computer. So sorry for all this. We'll be right back. Sorry.
back again. So I was just wondering if Jesse's still here. Maybe not. Okay then. Ryan, it seems like we have a 0.1 difference in the score again. So we just wanted to double, triple make sure, okay? That okay, but they're both gonna get gold medal anyway. So that's fine. We will just check again and then I'll be back in like 2 minutes, okay? Sorry to keep everyone waiting.
Is there music?
There's music.
Yeah,
Huh?
I was playing
Oh.
background music.
Ryan, you might have just copyrighted
Copyrights, right?
strike our stream.
Well, we can just get rid of that at the end, right?
Okay.
And it's YouTube within
Yes,
YouTube.
it's YouTube. All right, so
All right, back to you guys.
I think we are ready. Okay, let's just make sure the teams are here. Like, do we have people here? Okay, Dave, can you send a message in the general
Yeah, sure.
channel? Tell the teams, even if their ranking is not too high, to join because they might get an individual award. Let's pin all of them. I will go ahead and share my screen. All right, hopefully people can see my screen. Ryan, Dave, Andrew, should we get started?
Yep.
All right, then let's get started. So everyone, welcome to the closing / award ceremony of the 6th Canadian Young Physicists Tournament 2022. And I just want to introduce our partner, U of T Physics, and also our parent organization, STEM Fellowship. So first, we will begin by announcing our individual awards. And we will invite Professor Bailey. So I will give an introduction of Professor Bailey again. So Professor Bailey is a professor of physics at the University of Toronto. He is an experimental particle physicist. He's interested in understanding scientific uncertainties and is passionate about physics education. He runs the Advanced Physics Lab and the Electronics Lab courses in the department, and he is the chair of the U of T Physics Outreach Committee. He's also a member of the CaYPT Problem Selection Committee. And U of T Physics has been our partner since the beginning of CaYPT in 2017, and they hosted the CaYPTs before the pandemic, and we've always worked closely as we switched to online since 2021. And we will invite Professor Bailey to introduce our Best Theory and Best Experiment awards. So first we'll introduce a Best Experiment award. Professor Bailey.
Okay, thank you. So the Best Experiment awards recognize the most creative and effective experimental setup. And these awards are nominated by the jurors and verified by the CaYPT committee. And before announcing the best experiment, I didn't have a chance to watch all the matches, but I did catch the last few. And I'm always so impressed with the experimental abilities here. And the last two, I was immediately thought, we have advanced lab experiments taken by our third and fourth year engineering science and physics students that are really closely related to what you were doing today. We have an experiment called fractal viscous figuring, which is very closely related to the exploding droplets, really closely. And we have a conductivity experiment, which is really closely related to the conductivity experiment you did. So you should all be very proud of yourself. You can come into the advanced lab almost right now and do good work, it seems. Anyway, so the Best Experiment Award this year is awarded to Oscar Sun from Team Schwarzschilder in the report of Problem D bimetallic oscillator. So congratulations, Oscar.
Congratulations, Oscar. And next we'll move on to the Best Theory Award.
So the best theory award recognizes the most in-depth and unifying theoretical analysis of the phenomena. And again, I'd like to emphasize, I'm really impressed with the level of theoretical thought that's given in many of the presentations. So the best theory award this year is given to Chia-Lu Chen from Team UTS Power Rangers in the report of problem B, ring on the rod.
Congratulations.
Congratulations, Chia-Lu.
All right. And we also have our Student Leadership Award. And for this, I want to welcome Dr. Sasha Nokovic. Dr. N is the founder and president of STEM Fellowship and the editor-in-chief of the STEM Fellowship Journal. He is also a recipient of the Prime Minister Award for Teaching Excellence in STEM. And Dr. N will tell us about our parent organization, STEM Fellowship, a little bit, and then also present the Mohammed Asadi Lari Leadership Award. And welcome, Dr. N.
Thank you, and I'm really honored to speak to such an esteemed audience of actually a future of the national physics, I believe, and science altogether. So STEM Fellowship is a community of students, educators, and industry that creates opportunities for peer learning and open science. STEM Fellowships help students to develop new skills, to analyze and learn from enormous amount of data around them and become agents of change. It is achieved by fostering independent students learning outside the traditional classroom. We connect students and foster future thought leaders across Canada and around the world through ambassadors, university branches, high school chapters, and partnership. We provide high school students and invite you to take advantage of the opportunity of getting your first scholarly publication with the STEM Fellowship Open Access peer-reviewed journal published by Canadian Science Publishing and NRC Research Press. We foster inclusion and diversity in STEM fields by creating mentorship and research opportunities for students from communities traditionally underrepresented in STEM. We deliver unique experiential learning programs in scholarly communication, data science, for high school and undergraduate students. So I believe on your pathway, we hope to see you participating in STEM fellowship programs once you are in universities. And it is my privilege to present the Mohammed Asadi Lari Leadership Award, which is named after the student co-founder of STEM Fellowship and the person who brought CaYPT, well, who started CaYPT. He was IYPT participants from Iran, and when he joined STEM Fellowship, he was the one who actually started CaYPT. He and his sister passed away in tragic flight 752 incident in 2020. It's a great loss for our community and CaYPT. Mohammed Asadi Lari Leadership Award recognizes extraordinary leadership and commitment. We will present this award to 3 students from 2 different teams. It is nominated by CaYPT Student Resources Team and is verified by leadership of CaYPT Committee. So Mohammed Asadi Lari Leadership Award goes to Tianhong Si from Team Schroeder's Litter. As first-time participant, he built a team from students from 3 provinces, BC, Manitoba, and Ontario, and secured a teacher supervisor. His passion, dedication, and commitment are outstanding. The other two awards are presented to Olivia Zhang and Zifan Yi. Also, as first-time participants, Zifan contacted CaYPT committee about her interest in competition and built a team within a week. She had to step away from a leadership position, and Olivia shared the responsibility to run the team and led her team to an impressive ranking in the tournament. I'm happy to see these brilliant future leaders of our national and international science recognized and participate in our competition.
Congratulations to Tian, Olivia, and also Zifan. Really good work leading your teams. It's incredible that as first-time participants, you're able to like bring up a team, you know, whether from like different provinces or starting a team within a week. It's a really impressive achievement. So next, I guess we will move on to the team awards, which is our medals, right? We will have Andrew present our participation awards in order of ranking. Andrew, you're there?
Yes.
Okay, so.
Okay, so first we have team. Thank you guys so much for all of the hard work that you put into our tournament, and we hope to see you next year.
That's Team Vector Masters from St. Michael's University School in British Columbia.
Next, we have Team WL Mac from William Lyle Mackenzie CI from Ontario. Thank you guys all for your hard work. Next, we have Team Untitled from St. Michael's University School in British Columbia. Thank you once again for all of your effort that you've put into CaYPT 2022. Next, Team Synapse from St. Michael's University School, Province, British Columbia. Thank you guys for participating this year. Next, Team Nucleosynthesizers from Upper Canada College in Ontario. Thank you for participating in this year's CaYPT 2022. Then we have Team Schrodinger's Litter, a mixed team spanning British Columbia, Manitoba, and Ontario. We would like to thank you guys for not only participating, but also being able to form such a diverse team for CaYPT 2022. Next, Team MGCI from Mark Garneau CI and from Ontario. Thank you all for participating in CaYPT.
Next, we will present our bronze medals, and Dave will do that. Dave, you're there?
Yep.
All right.
So our first bronze medal goes to Team Havergal, and perhaps one of the most outstanding accomplishments was to put a team together in a week and still be able to clinch a bronze medal in their first year participating. So outstanding work. Congratulations. The second bronze medal goes to Team UTS Newton. Thank you all for this amazing achievement and for your hard work. The third bronze medal goes to Team UTS Shrimskis. You guys are approaching silver, so that's really nice to see. Thank you for participating and all your hard work too. And the final bronze medal, very close to silver. It was very close in the end, but goes to Team UTS Power Rangers. Congratulations on your achievement.
And next we'll move on to silver medals. And the first silver medal that I will present to is to Team Optics. So congratulations for winning a silver medal in CaYPT 2022. I saw that from your score ranking that you had a very good like upward trend in terms of your marks over the 5 rounds. So congratulations, they're an independent team from the province of Ontario. And next we have our second silver medal recipient team, and they are one of the 3 teams in the final physics match. So the team that will receive a silver medal is Team Victoria Park Collegiate Institute. And congratulations to you guys. You guys worked really hard on your problems, and you guys have done a wonderful job in the final physics match, as you will probably see in the streams that will be published soon. After this is done, you can go back to it. And then for our gold medals, that is between the top 2 teams that has competed in the final physics match. And just to note, these 2 teams have gotten a really, really, really close score in the final physics match, only by 0.1. Okay, and upon our calculations, you know, me, Andrew, and also Dave, we've like verified everything. We've looked at all the score sheet that we had, and then we present the gold medal, first gold medal, to Team UTS Bernoulli. Congratulations. And finally, our second gold medal and the winner of CaYPT 2022 is Team Schwarz children from a hybrid school, they call it, and from the province of Ontario. So congratulations, you guys have done really well in the final physics match. Excellent reports, opposition, and review. All right, so that will conclude the award ceremony of the 6th Canadian Young Physicists Tournament 2022. Just a concluding remark. So I would like to thank all the participants for all the time that you have spent working on these problems. As Professor Bailey and Dr. N has said, it is truly incredible that you guys are able to do this at such a young age, and with various like equipment and resources limitations. And also, I really enjoyed the time that I spent talking to you guys during the office hour that we had yesterday, I believe. And I know that some of you guys did not get a lot of sleep. So hopefully after the competition, you will get some rest. And apart from the participants, I also want to thank all of our amazing team leaders. Without their supervision and guidance, this would not have been possible. And we have some like really dedicated either teachers or parents, and some of them has judged in our tournament as well. So thank you guys so much for spending the time to be on our jury, and you presented some excellent feedback to all of the teams. And I would also like to thank all of the jurors, that are not the team leaders. These are mostly graduate students from the physics department of U of T, and you guys have spent your personal time to look at these presentations by these young physicists. I really appreciate your work, and also the excellent feedback that you have given to them. And I'm sure this will help them tremendously, not only in the individual selection stage, which will come up, and to decide who will enter the CaYPT National Camp, and also help them with their physics learning in the long run. And in terms of administrative staff, I guess I would like to thank everyone in the committee. So that's Dave, which is our student resources team lead, and also the associate director of the committee. Also Andrew, you guys know him as the mastermind behind our brilliant system, which helped us so much with calculating the bands and organizing the entire tournament, along with his team member Leo, which they worked really hard to do extra testing to make sure that the system functioned as well as it could, right? And also 2 of the members that you guys have not seen, Xiong and also Arsha. Xiong is our sponsorship and partnership team lead, and she was really helpful in helping us find a lot of jurors and supports. And Arsha is our student resources team member, and he's worked really hard to make sure that we can provide a lot of resources to the students. He's working on a project which is a computational physics crash course, and we will be introducing that to all of the students on our YouTube channel in the next month or so, hopefully. And then also all of our committee members that also played a role in the competition itself. I would like to thank Daniel, Tracy, Olivia, and also John. They are participants themselves, but during the preparation, they've offered a lot of interesting feedback, and they help run our YouTube channel, Instagram account, student SOP project, and also the student resources, the crowdsourced reference kit that many of you relied on. And finally, I would just like to thank again Professor Bailey and Dr. N for spending your time joining us at the opening and the award ceremonies. I think it's really good that you guys sort of conveyed your passion of education and STEM and physics to the students, and I'm sure that will inspire them to pursue further studies and maybe even a career in STEM. Yeah. So finally, an announcement about some of the next steps in terms of our yearly cycle, right? So after the competition, we have an individual selection round, which we will select the members that will join us at the CaYPT National Camp. So how that's going to work is that everyone that's participated in the CaYPT are eligible to submit their own presentation for judging. We will have a very detailed form that will allow you to declare your contributions. And if you're interested, please pay attention to our website. Also, stay in the Discord channel. We will announce the updates on that step there as well. And as Ryan has told me as a juror, he saw a lot of excellent presentations. So we sincerely encourage everyone to apply. And I think I forgot to thank Ryan. Ryan is our sort of the only, I guess, true adult in our CaYPT committee. He is the representative of Canada at the International Young Physicists Tournament, and he has provided us with a lot of help in terms of administration and in particular technical support in terms of Zoom. And he's also acted as a juror, which really helped to alleviate our juror shortage this year. So yeah, if you guys have any questions or you want to stay in the call to have a bit of an after party, feel free to do so. But this will conclude the 6th Canadian Young Physicists Tournament 2022. And hopefully everyone had a great time. Thank you.
Should I stop the stream?